Tonight, we journey through humanity's long conversation with this most gentle yet powerful of nature's forces, the invisible hand that shapes galaxies and guides raindrops home. In the warm evening air of ancient Babylon, some 4,000 years ago, astronomers climbed the steps of ziggurats, those magnificent stepped temples that reached toward the heavens. These patient observers of the night sky were among the first humans to systematically record the movements of celestial bodies, though they couldn't have known they were documenting gravity's choreography. They watched planets trace their paths across the star-studded darkness, noted the moon's faithful journey around Earth, and began to sense that something profound governed these movements. The Babylonians developed sophisticated mathematical models to predict eclipses and planetary positions. Their cuneiform tablets, pressed into soft clay and baked hard in the desert sun, contain calculations that reveal an understanding that celestial bodies followed predictable paths. They called the planets wandering stars, distinguishing them from the fixed stars that maintained their positions relative to one another. What they were observing, without the vocabulary to name it, was gravity's influence on massive bodies moving through space. Meanwhile, in ancient Egypt, engineers were grappling with gravity in more practical ways. The construction of the pyramids required an intimate understanding of weight, balance, and the tendency of objects to fall. Egyptian builders developed ingenious methods to move massive stone blocks, some weighing as much as 80 tons, up ramps and into precise positions. They understood that objects had weight, that this weight pulled them downward, and that overcoming this downward pull required specific amounts of force. The ancient Egyptians also observed gravity's effects on water. The annual flooding of the Nile, which brought life-giving silt to their fields, demonstrated how water always flows downhill, seeking the lowest point. Their irrigation systems, some of which still function today, were masterworks of gravitational engineering. They carved channels at precise angles, understanding intuitively that water would flow faster down steeper slopes and slower down gentler ones. In ancient India, philosophers of the Vaisheshika school of thought, dating back to around the 6th century BCE, proposed remarkable ideas about the nature of falling objects. The sage Canada, whose name literally means atom eater, suggested that all matter was composed of indivisible particles called anu or atoms. More remarkably, he proposed that objects fall toward the earth because of a force he called gurutva, meaning heaviness or gravity. This wasn't merely philosophical speculation. Canada attempted to describe why smoke rises while stones fall, recognizing that different substances behave differently under the influence of this mysterious force. The Vaisheshika texts describe experiments with falling objects, noting that all things, regardless of their composition, fall toward the earth when released. They observed that this falling motion accelerates, though they lacked the mathematical tools to quantify this acceleration. These ancient Indian thinkers were asking the right questions. What causes objects to fall? Why do they fall toward Earth specifically? Is there something special about Earth that attracts objects? Ancient Chinese philosophers approached the question from yet another angle. The concept of qi, the fundamental energy or life force that flows through all things, included ideas about why objects behave as they do. The Chinese recognized that heavy objects sink while light objects rise, attributing this to the natural tendency of all things to seek their proper place in the cosmic order. The heavy yin energy naturally moved downward, while the light yang energy rose upward. During the Han Dynasty, around 2,000 years ago, Chinese scholars made remarkably accurate observations about tides, correctly attributing them to the influence of the moon. The scholar Wang Chong wrote in his work, Lunheng, that tides rise and fall with the moon's position, demonstrating an understanding that celestial bodies could exert influence across vast distances. This was a profound insight, suggesting that the force causing objects to fall might be related to the forces governing celestial movements. The ancient Greeks, those tireless questioners of nature, developed the first systematic theories about why objects fall. Thales of Miletus, often considered the first philosopher in the Western tradition, proposed around 600 BCE that water was the fundamental substance of all matter. He observed that water could exist as solid ice, liquid water, and gaseous steam, and reasoned that all matter might be water in different forms. While this theory was incorrect, it represented one of humanity's first attempts to find universal principles underlying natural phenomena. Anaximander, a student of Thales, proposed something even more abstract: the apeiron, or the boundless, an infinite and eternal substance from which all things emerged and to which they returned. He suggested that the Earth floated freely in space, held in position by being equidistant from all other celestial bodies. This was a remarkable intuition, recognizing that Earth didn't need to rest on something solid, but could be suspended in space. Empedocles, living in Sicily around 450 BCE, introduced the concept of love and strife as cosmic forces. Love brought things together, while strife separated them. When he described how the four elements, earth, water, air, and fire, naturally moved to their proper places, with earth and water moving downward and air and fire moving upward, he was describing what he saw as love, drawing like to like. This poetic description contained the seed of an important idea that there might be attractive forces operating in nature. The atomists Leucippus and Democritus proposed that all matter consisted of indivisible particles called atoms moving through void. They suggested that atoms had weight and that heavier atoms naturally moved downward through the void. This was perhaps the first mechanistic explanation for falling motion, removing the need for purpose or design and suggesting that falling was simply what heavy atoms did. But it was Aristotle, that giant of ancient philosophy, whose ideas about falling bodies would dominate Western thought for nearly 2,000 years. Aristotle rejected the atomist's void, arguing that nature abhors a vacuum. He proposed that the universe was divided into two regions: the sublunary sphere below the moon's orbit, where things were imperfect and changeable, and the superlunary sphere beyond, where everything was perfect and eternal. In Aristotle's physics, every object had a natural place determined by its composition. Objects made primarily of the element earth belonged at the centre of the universe, which happened to be where Earth was located. Water belonged in a sphere surrounding Earth, air in a sphere above water, and fire in the highest sublunary sphere. When displaced from their natural positions, objects would move in straight lines back toward where they belonged. A stone falls because it contains earth and seeks to return to the centre. Smoke rises because it contains fire and air, seeking their natural places above. Aristotle also proposed that heavier objects fall faster than lighter ones, a claim that seemed to match everyday observation. After all, a stone clearly falls faster than a feather. He developed mathematical relationships, suggesting that an object twice as heavy would fall twice as fast. This intuitive but incorrect idea would persist for centuries, accepted as truth by scholars across Europe and the Islamic world. The ancient observations weren't limited to philosophical speculation. Practical applications of gravitational knowledge appeared in remarkable engineering projects worldwide. The Romans built aqueducts that carried water for hundreds of miles, maintaining precise gradients that allowed water to flow continuously from mountain springs to urban fountains. The Pont de Gare in southern France, standing nearly 50 metres high, maintains a gradient of just 34 centimeters per kilometer, a testament to Roman engineers' understanding of how gravity moves water. In ancient Peru, the Inca developed sophisticated agricultural terraces that used gravity-fed irrigation systems. Their understanding of water flow and pressure allowed them to build fountains and channels that still function today at sites like Machu Picchu. The precision of these water systems reveals a deep practical knowledge of how gravity affects fluid motion. Ancient Polynesian navigators, voyaging across vast stretches of the Pacific Ocean, understood tides and currents in ways that revealed gravity's influence on Earth's oceans. They knew that tides varied with the moon's phases, being strongest during new and full moons when the sun and moon aligned. This knowledge, passed down through generations in songs and stories, allowed them to navigate thousands of miles of open ocean. The Antikythera mechanism, recovered from a shipwreck off the Greek island of Antikythera and dating to around 100 BCE, represents perhaps the most sophisticated ancient understanding of celestial mechanics. This intricate bronze device, containing at least 30 meshing gears, could predict the positions of the sun, moon, and planets, as well as eclipses. Its creators understood the complex orbital periods of celestial bodies, though they interpreted these movements within a geocentric model of the universe. As we look back at these ancient observations and theories, we see humanity's first attempts to understand the invisible force that shapes our daily experience. Every culture that looked up at the night sky or watched water flow downhill was observing gravity's effects. The questions they asked: why do things fall? What holds the moon in the sky? Why do tides rise and fall? Were the right questions, even if their answers were incomplete. These ancient thinkers laid the groundwork for everything that would follow. Their careful observations of falling objects, flowing water, and celestial movements provided the data that later scientists would use to develop mathematical theories of gravitation. Their philosophical frameworks, while often incorrect in detail, established the principle that natural phenomena could be understood through reason and observation. The transition from mythological explanations to naturalistic ones represented one of humanity's great intellectual achievements. Instead of attributing falling motion to the whims of gods or spirits, ancient philosophers sought mechanical explanations based on the properties of matter itself. This shift in thinking, from supernatural to natural causation, was essential for the development of science. The dominance of Aristotelian physics throughout the medieval period created a universe that was comfortable and comprehensible to human intuition. In the centuries following Aristotle's death in 322 BCE, his ideas spread throughout the Hellenistic world, were preserved and expanded by Islamic scholars during Europe's Dark Ages, and eventually returned to European universities, where they became orthodox doctrine. This wasn't mere intellectual stubbornness. Aristotle's physics offered a complete, internally consistent explanation for observed phenomena that aligned with common sense and religious doctrine. In Alexandria, that great centre of ancient learning, scholars at the famous library refined and catalogued Aristotelian physics alongside competing theories. The mathematician and engineer Archimedes, working in Syracuse in the 3rd century BCE, made discoveries about buoyancy and leverage that would later prove crucial to understanding gravity, though he worked within an essentially Aristotelian framework. His principle of buoyancy explained why some objects float while others sink, adding mathematical precision to Aristotle's qualitative descriptions. Archimedes' work on centres of gravity represented a crucial advance. He showed that every object behaves as if its entire weight were concentrated at a single point, what we now call the centre of mass. This insight allowed for precise calculations in engineering and laid groundwork for later understanding of how gravity acts on extended objects. His famous boast, "Give me a place to stand, and I will move the earth," revealed an understanding that gravity's effects could be overcome through mechanical advantage. The Roman engineer Vitruvius, writing in the 1st century BCE, applied Aristotelian principles to practical problems of architecture and engineering. His treatise De Architectura described how to construct buildings that would stand against gravity's constant pull, how to design arches that distributed weight efficiently, and how to build aqueducts that used gravity to deliver water across vast distances. Roman engineering success seemed to validate Aristotelian physics in the most practical way possible. As the Roman Empire declined, the centre of scientific learning shifted eastward. Islamic scholars in Baghdad, Cairo and Cordoba preserved and expanded upon Greek knowledge. The 9th century Persian mathematician and astronomer Muhammad ibn Musa al-Khwarizmi developed algebra partly to solve problems involving projectile motion, though he still accepted Aristotle's basic framework of natural motion. The 11th century Persian polymath Ibn al-Haytham, known in the West as al-Hazan, made crucial contributions to the understanding of motion. Working in Cairo, he conducted experiments with falling bodies and projectiles, developing early ideas about inertia that would later influence Galileo. He questioned Aristotle's claim that heavier objects fall faster, noting that the difference in fall rates between heavy and light objects wasn't as dramatic as Aristotelian theory predicted. Ibn al-Haytham's method was revolutionary. Rather than simply reasoning from first principles, as Aristotle had done, he insisted on experimental verification. He dropped objects from heights, rolled balls down inclined planes, and carefully measured their motion. His Book of Optics described experiments that anyone could repeat, establishing reproducibility as a cornerstone of scientific investigation. The Persian scholar Ibn Sina, known as Avicenna in the West, proposed around 1020 CE that a moving object has an inclination, or male, that keeps it moving even after the original force is removed. This concept of impressed force was a step toward understanding inertia and represented a significant departure from Aristotle's idea that motion required continuous application of force. Avicenna suggested that celestial bodies moved eternally because nothing in the heavens could remove their male. In Islamic Spain, the 12th century philosopher Ibn Rushd, called Averroes in Latin, wrote extensive commentaries on Aristotle that would profoundly influence European thought. While generally defending Aristotelian physics, Averroes raised important questions about the nature of motion and force. He wondered why celestial bodies moved in circles eternally, while earthly objects quickly came to rest, suggesting there might be different types of matter with different natural behaviours. When Aristotelian texts, accompanied by Islamic commentaries, arrived at European universities in the 12th and 13th centuries, they transformed intellectual life. Thomas Aquinas synthesized Aristotelian physics with Christian theology, creating a worldview where God worked through natural laws rather than constant miraculous intervention. The falling of a stone became not just a physical phenomenon, but a reflection of divine order. Medieval European scholars, working within this Christianized Aristotelian framework, made their own contributions. At Oxford University's Merton College, in the 14th century, a group of scholars known as the Oxford Calculators developed mathematical descriptions of motion. Thomas Bradwardine, William Heytesbury, and Richard Swineshead created the mean speed theorem, showing that a uniformly accelerating body travels the same distance as a body moving at constant velocity equal to the accelerating body's average velocity. The Oxford Calculators' work was highly abstract, focusing on mathematical relationships rather than physical experiments. They distinguished between dynamics, the study of forces causing motion, and kinematics, the description of motion itself, a distinction that remains fundamental to physics. Their mathematical approach to motion, while still embedded in Aristotelian metaphysics, pointed toward the quantitative methods that would eventually overthrow Aristotle's physics. In Paris, John Buridan developed the theory of impetus in the 14th century, building on Avicenna's earlier work. Buridan proposed that a thrown object receives an impetus proportional to its weight and velocity. This impetus maintains the object's motion until resistance depletes it. Unlike Aristotle's theory requiring continuous contact with a mover, impetus theory allowed for motion through empty space, a crucial conceptual advance. Buridan's student Nicole Oresme went even further, suggesting that the Earth might rotate daily rather than the heavens revolving around it. He argued that it was simpler to imagine Earth spinning than the entire universe rotating at enormous speed. While Oresme ultimately rejected this idea for theological reasons, his willingness to consider it showed that medieval scholars weren't merely passive recipients of ancient wisdom. The 15th and 16th centuries saw increasing challenges to Aristotelian orthodoxy. Nicolaus Cusanus proposed that the universe might be infinite, with no absolute centre, undermining the special status of Earth in Aristotelian cosmology. Leonardo da Vinci conducted experiments with falling bodies, noting that air resistance affected light objects more than heavy ones, suggesting that in the absence of air, all objects might fall at the same rate. The Polish astronomer Nicolaus Copernicus revolutionized cosmology with his heliocentric model, published in 1543. By placing the Sun at the centre of the solar system, Copernicus challenged the fundamental Aristotelian distinction between earthly and celestial realms. If Earth was just another planet orbiting the Sun, perhaps the same physical laws applied everywhere in the universe. The Danish astronomer Tycho Brahe, working in the late 16th century, made precise observations that revealed problems with both Aristotelian and Copernican models. His detection of a supernova in 1572 and careful tracking of comets showed that the heavens weren't unchanging as Aristotle had claimed. These observations suggested that celestial and terrestrial physics might be unified, subject to the same fundamental laws. It was in this context of accumulating anomalies and conceptual tensions that Galileo Galilei began his revolutionary work. Born in Pisa in 1564, Galileo inherited a world where Aristotelian physics was increasingly strained but still officially dominant. His genius lay not just in conducting decisive experiments, but in reimagining the fundamental nature of motion itself. The famous story of Galileo dropping balls from the Leaning Tower of Pisa, while probably apocryphal, captures the essence of his challenge to Aristotelian physics. Whether or not he performed this public demonstration, Galileo certainly conducted careful experiments with falling bodies. Using inclined planes to slow the motion enough for accurate measurement, he discovered that falling objects accelerate uniformly, gaining the same amount of velocity in each unit of time. Galileo's inclined plane experiments were masterpieces of experimental design. By rolling balls down planes at various angles, he could study accelerated motion in detail. He measured time using water clocks and his own pulse, marking distances travelled at regular intervals. His results showed that distance travelled was proportional to the square of elapsed time, a mathematical relationship incompatible with Aristotelian physics. More fundamentally, Galileo recognized that in the absence of air resistance, all objects would fall at the same rate regardless of their weight. He reasoned that if a heavy object fell faster than a light one, then tying them together should produce an intermediate fall rate, but the combined object would be heavier than either component and should therefore fall faster than both. This logical contradiction showed that Aristotle's premise must be false. Galileo's principle of inertia transformed understanding of motion. Rather than requiring explanation for why objects move, as Aristotle had assumed, Galileo argued that uniform motion was a natural state requiring no cause. Only changes in motion acceleration or deceleration needed explanation. This shift from asking what keeps it moving to what changes its motion was revolutionary. The concept of inertia explained many puzzling phenomena. Why doesn't a ball dropped from a ship's mast fall behind the ship? Because it shares the ship's forward motion and maintains it while falling. Why can we jump straight up on a moving Earth without landing far behind our starting point? Because we share Earth's motion. Galileo showed that motion was relative, depending on the observer's frame of reference. Galileo's telescopic observations, beginning in 1609, provided additional evidence against Aristotelian cosmology. The mountains on the moon showed it wasn't a perfect sphere. The moons of Jupiter demonstrated that celestial bodies could orbit centres other than Earth. The phases of Venus proved it orbited the Sun. These observations suggested that celestial bodies were physical objects like Earth, subject to the same laws. The reaction to Galileo's work was complex and often hostile. The Catholic Church, having adopted Aristotelian physics as compatible with Scripture, saw challenges to Aristotle as potential heresy. Galileo's trial and house arrest in 1633 demonstrated the institutional resistance to new ideas about gravity and motion. Yet his ideas spread throughout Europe, inspiring a new generation of natural philosophers. Galileo's student Evangelista Torricelli continued experimental investigations, inventing the barometer and demonstrating that air has weight. This showed that we live at the bottom of an ocean of air, held down by gravity just like water in the sea. The vacuum above the mercury in Torricelli's tube proved that Aristotle was wrong about nature abhorring a vacuum. The French philosopher René Descartes, working in the early 17th century, attempted to build a complete mechanical philosophy to replace Aristotelianism. Descartes proposed that all motion resulted from matter pushing against matter in an infinite plenum. Gravity, in his view, resulted from vortices of subtle matter pushing objects toward Earth's centre. While incorrect, Descartes' mechanical approach influenced how later thinkers conceptualized gravitational attraction. The journey from Aristotle to Galileo represents one of the great intellectual transformations in human history. Over 2 millennia, humanity moved from a cosmos of natural places and purposes to one of mathematical laws and mechanical forces. The comfortable, intuitive universe where stones fell because they sought their natural place gave way to a strange new world where motion was relative and required no explanation. This transformation wasn't merely scientific but deeply philosophical. If heavy and light objects fall at the same rate, then weight isn't an intrinsic property determining behaviour. If terrestrial and celestial realms obey the same laws, then Earth isn't fundamentally different from other cosmic bodies. If motion is relative, then there's no absolute rest or absolute position. These ideas challenged not just scientific theories, but basic assumptions about humanity's place in the universe. The experimental method that emerged during this period, the careful measurement, mathematical analysis, and reproducible testing that Galileo exemplified, became the foundation of modern science. Rather than deducing how nature must behave from first principles, scientists began observing how it actually does behave and finding mathematical patterns in those observations. Yet even as Galileo's experiments demolished Aristotelian physics, they raised new questions. If all objects fall at the same rate, what exactly is this tendency to fall? If the moon orbits Earth and Jupiter's moons orbit Jupiter, what invisible connection maintains these orbits? If motion is relative to what? The stage was set for Isaac Newton to synthesize these discoveries into a universal theory of gravitation that would transform human understanding of the cosmos. The year 1666 would later be called Isaac Newton's Annus Mirabilis, his miraculous year, though the 23-year-old Newton himself, isolated at his family's farm in Woolsthorpe, while Cambridge University closed due to plague, had no idea he was revolutionizing humanity's understanding of the universe. The story of the falling apple, whether literally true or metaphorically perfect, captures a moment when disparate observations suddenly crystallized into universal law. Newton himself would later tell multiple versions of the apple story to different people. To his friend William Stukeley, he described sitting in contemplative mood when the fall of an apple occasioned the notion of gravitation. To his niece's husband, John Conduit, he mentioned how the apple's fall made him wonder why it fell straight down rather than sideways or upward. The power of the story lies not in its literal truth, but in its representation of Newton's great insight. The force pulling an apple to Earth might be the same force keeping the moon in its orbit. This connection between terrestrial and celestial motion was Newton's revolutionary leap. Galileo had shown that projectiles follow parabolic paths. Johannes Kepler had discovered that planets orbit in ellipses. Newton realized these were different manifestations of the same phenomenon. A cannonball fired horizontally from a mountain would fall to Earth in a parabolic arc. Fire it faster, and it travels farther before hitting the ground. Fire it fast enough, and it would fall around Earth's curve at the same rate Earth's surface curves away. It would be in orbit. Newton's thought experiment of a cannon on a mountain high enough to be above Earth's atmosphere was brilliant in its simplicity. Each increase in the cannonball's velocity would carry it farther around Earth before it struck the ground. At precisely the right velocity, the cannonball would fall toward Earth at exactly the rate needed to maintain a circular path. The moon, Newton realized, was simply a cannonball that never landed, perpetually falling toward Earth but moving sideways fast enough to continuously miss. The mathematical framework Newton developed to describe this universal gravitation was unprecedented in its power and precision. Building on his invention of calculus, which he called the method of fluxions, Newton could handle continuously changing quantities in ways previous mathematicians couldn't. Where Galileo could describe how objects accelerate when falling, Newton could explain why they accelerate and predict exactly how any object would move under gravity's influence. The inverse square law, the mathematical heart of Newton's theory, stated that gravitational force decreases with the square of distance. Double the distance between two objects, and the gravitational force becomes 1/4 as strong. Triple the distance, and it becomes 1/9 as strong. This simple mathematical relationship explained phenomena from falling apples to planetary orbits with stunning accuracy. Newton didn't arrive at the inverse square law through pure deduction. He knew from Kepler's third law that the square of a planet's orbital period was proportional to the cube of its average distance from the Sun. Using his new calculus, Newton showed that this relationship required a force that decreased with the square of distance. The mathematical elegance was breathtaking. Kepler's empirically discovered laws of planetary motion emerged naturally from Newton's theory of universal gravitation. The universality of Newton's law was its most radical aspect. The same equation described the fall of a raindrop, the arc of a thrown stone, the orbit of the moon, and the paths of comets. Mass attracted mass everywhere in the universe, at all scales, following the same mathematical law. This was a unification beyond anything previously imagined, collapsing the ancient distinction between earthly and heavenly realms into a single, mathematically describable cosmos. Newton's Principia Mathematica, published in 1687 after much encouragement from astronomer Edmund Halley, presented his theory in rigorous mathematical detail. The work was deliberately difficult, written in Latin and using geometric proofs rather than his more powerful calculus methods, partly to avoid plagiarism and partly to limit his audience to serious mathematicians. Even so, its impact was immediate and profound among those capable of understanding it. The Principia began with 3 laws of motion that remain fundamental to physics. The first law, the principle of inertia, stated that objects at rest stay at rest, and objects in motion stay in motion, unless acted upon by a force. This formalized Galileo's insights about motion requiring no explanation. The second law, often written as Fma, related force to mass and acceleration, providing a quantitative measure of how forces change motion. The third law, that every action has an equal and opposite reaction, explained how forces always come in pairs. These laws of motion, combined with the law of universal gravitation, allowed Newton to derive Kepler's laws of planetary motion from first principles. Where Kepler had found patterns in astronomical data, Newton explained why those patterns existed. Planets moved in ellipses because that's the shape produced by an inverse square force. They swept out equal areas in equal times because angular momentum was conserved. Their periods related to their distances in precise mathematical ratios determined by the strength of solar gravity. Newton's theory explained countless phenomena that had puzzled previous thinkers. The tides resulted from the differential gravitational pull of the Moon and Sun on Earth's oceans. The slight flattening of Earth at its poles came from the balance between gravity and centrifugal force due to Earth's rotation. The precession of Earth's axis, causing the celestial poles to trace circles over 26,000 years, resulted from gravitational torques exerted by the Sun and Moon on Earth's equatorial bulge. The predictive power of Newtonian mechanics was demonstrated spectacularly when Edmund Halley used it to predict the return of the comet that now bears his name. By calculating the gravitational influences of Jupiter and Saturn on the comet's orbit, Halley predicted it would return in 1758, which it did, 16 years after his death. This successful prediction, spanning decades and depending on precise calculation of multiple gravitational influences, validated Newton's theory in the public imagination. Newton's concept of absolute space and time provided the framework within which gravitation operated. He envisioned space as an infinite, three-dimensional container existing independently of the matter within it. Time flowed uniformly throughout the universe, the same for all observers. Gravity acted instantaneously across any distance through this absolute space, though Newton himself was troubled by this action at a distance. The philosophical implications of Newton's system were profound and controversial. If the universe operated according to mathematical laws, what room was there for divine intervention? Newton himself was deeply religious and saw his laws as describing how God maintained cosmic order. He spent as much time on theology and alchemy as on physics, seeking to understand God's plan in all its aspects. The clockwork universe his physics implied, running according to immutable laws, raised questions about free will and determinism that philosophers still debate. Critics of Newton's theory raised important objections. Gottfried Leibniz, who independently invented calculus and engaged in bitter priority disputes with Newton, argued that absolute space and time were meaningless concepts. Space and time, Leibniz contended, were merely relationships between objects and events, not independent entities. This philosophical disagreement would resurface centuries later in Einstein's relativity. The action at a distance problem particularly troubled thoughtful physicists. How could the sun influence Earth's motion across 93 million miles of empty space? Newton acknowledged he had no mechanism for gravitational attraction, famously stating, "Hypotheses non fingo, I frame no hypotheses." His theory described what gravity did with mathematical precision, but not what gravity was. Despite these philosophical puzzles, Newtonian mechanics achieved triumph after triumph. Pierre-Simon Laplace refined Newton's mathematics and showed that the solar system was stable over long periods, addressing worries that accumulating gravitational perturbations might eventually destroy planetary orbits. Laplace famously told Napoleon that his celestial mechanics needed no hypothesis of God, to which Napoleon reportedly replied, "But it is a beautiful hypothesis nonetheless." The discovery of Neptune in 1846 provided perhaps the most dramatic confirmation of Newton's theory. Astronomers had noticed that Uranus, discovered in 1781, wasn't following its predicted orbit. Urbain Le Verrier in France and John Couch Adams in England independently calculated that gravitational pull from an undiscovered planet could explain the discrepancies. When Johann Galle pointed his telescope to Le Verrier's predicted position, he found Neptune within 1 degree of the calculated location. Newton's theory also had profound practical applications. Ballistics calculations for artillery became precise sciences. Navigation improved as lunar positions could be predicted accurately. Engineers could calculate the forces in bridges and buildings with confidence. The Industrial Revolution was built partly on the foundation of Newtonian mechanics, as engineers designed machines knowing exactly how forces and motions related. The concept of gravitational potential energy emerged from Newton's work, though he didn't use that terminology. Lifting an object against gravity stores energy that can be released when the object falls. This understanding led to hydroelectric power, where falling water's gravitational energy turns turbines. It explained why comets speed up when approaching the sun and slow down when receding, converting gravitational potential energy to kinetic energy and back. Newton's universal gravitation revealed patterns at all scales. The same inverse square law governing planetary orbits described how binary stars dance around their common centre of mass. Entire galaxies unknown in Newton's time would later be understood as vast collections of stars held together by their mutual gravitation. Galaxy clusters and superclusters continued the pattern at ever larger scales. The success of Newtonian gravitation inspired confidence that all natural phenomena might yield to mathematical analysis. Electricity and magnetism, heat and light, chemistry and biology scientists approached each field, hoping to find their own universal laws. The scientific revolution Newton embodied changed not just our understanding of gravity, but our entire approach to understanding nature. Yet even in its triumph, Newtonian gravity contained seeds of its own overthrow. The orbit of Mercury, the innermost planet, showed a tiny discrepancy that couldn't be explained by gravitational influences from other planets. This perihelion precession, a mere 43 arcseconds per century, would eventually point toward the need for a new theory of gravitation. The speed of gravity also posed problems. If the sun suddenly vanished, Newton's theory suggested Earth would immediately fly off in a straight line. But how could Earth instantly know the sun had disappeared? As physicists in the 19th century established that light had finite speed, the idea of instantaneous gravitational effects became increasingly problematic. Newton transformed gravity from a tendency of objects to seek their natural places into a universal force described by precise mathematical laws. The falling apple and orbiting moon were united in a single framework that explained phenomena from raindrops to galaxies. His synthesis of terrestrial and celestial mechanics created the first truly universal physical theory, applicable everywhere in the cosmos. The Newtonian worldview dominated physics for over 2 centuries, and for most practical purposes, it remains accurate today. We still use Newton's equations to send spacecraft to other planets, to predict eclipses centuries in advance, and to understand the dynamics of stellar systems. The GPS satellites orbiting Earth require relativistic corrections, but their basic orbits follow Newtonian mechanics. Newton gave humanity a universe of clockwork precision, where future and past could be calculated from present conditions. His mathematics revealed order in apparent chaos, showing that complex phenomena emerged from simple laws. The falling apple became a symbol not just of discovery, but of the human ability to comprehend cosmic order through reason and observation. The triumph of Newton's gravitational theory left natural philosophers with a beautiful mathematical description, but a troubling conceptual mystery. How did massive objects influence each other across the vast emptiness of space? This question, which Newton himself acknowledged he couldn't answer, would occupy physicists for centuries and ultimately lead to revolutionary, new understandings of space, time, and gravity itself. In the decades following Newton's Principia, scientists and philosophers grappled with the mechanism of gravitational attraction. René Descartes had proposed that space was filled with invisible vortices of subtle matter that pushed planets in their orbits, but Newton's mathematics had demolished this mechanical explanation. The planets didn't move as they would if pushed by swirling fluids. They followed paths that required attractive forces directed toward the sun, not pushing forces from surrounding matter. The concept of force itself was philosophically troublesome. In everyday experience, forces required contact. You push a cart, the wind moves leaves, water turns a mill wheel. But gravity seemed to operate without any medium, without any physical connection between the attracting bodies. The sun somehow reached across 93 million miles of apparent nothingness to tug on Earth, and Earth simultaneously pulled back on the sun with equal force. Some natural philosophers proposed that space wasn't truly empty, but filled with an invisible, elastic medium called the ether. Perhaps gravity propagated through this ether, like waves through water or sound through air. But attempts to detect the gravitational ether or understand its properties failed. How could a medium rigid enough to transmit forces instantly be subtle enough that planets moved through it without resistance? The Swiss mathematician Leonhard Euler, working in the mid-18th century, made crucial mathematical advances in understanding gravitational effects, even without knowing gravity's mechanism. He developed the concept of the gravitational potential, a scalar field that assigned a number to every point in space, representing the gravitational potential energy per unit mass at that location. This was a profound abstraction. Empty space itself possessed mathematical properties determined by distant masses. Euler's potential field simplified many calculations. Instead of summing forces from every particle of matter in a complex object, physicists could calculate the potential field once and then easily determine the force on any test mass by taking the gradient of the potential. The mathematical elegance was undeniable, but it deepened the mystery. How did empty space know what potential value it should have? Joseph Louis Lagrange, working in the late 18th century, reformulated Newtonian mechanics in terms of energy rather than forces. His approach, now called Lagrangian mechanics, showed that objects moved along paths that minimized a quantity called action. This principle of least action suggested that nature operated according to optimization principles, as if objects somehow knew which path to take before taking it. Pierre-Simon Laplace extended Newton's work to show that gravitational influences propagated at finite speed would destabilize planetary orbits. His calculations demonstrated that if gravity travelled at any finite velocity, planets would spiral into the sun or fly off into space. This seemed to prove that gravitational effects must be instantaneous, adding to the mystery of how information about mass positions could travel infinitely fast. The German mathematician Carl Friedrich Gauss developed powerful mathematical tools for understanding gravitational fields in the early 19th century. Gauss's law for gravity stated that the total gravitational flux through any closed surface depended only on the mass enclosed within that surface. This was remarkable. You could determine the mass inside a region without looking inside, just by measuring the gravitational field on its boundary. Gauss's law revealed deep connections between geometry and gravity. The divergence of the gravitational field at any point equaled the mass density at that point, multiplied by a constant. Empty space had zero divergence, while matter created divergence proportional to its density. The gravitational field possessed geometric properties that encoded information about mass distribution throughout space. The Irish mathematician William Rowan Hamilton reformulated mechanics again in the mid-19th century, creating what's now called Hamiltonian mechanics. His approach treated position and momentum as independent variables evolving through phase space according to Hamilton's equations. This abstract mathematical framework would later prove crucial for understanding quantum mechanics and the quantum nature of fields. As the 19th century progressed, physicists developed increasingly sophisticated mathematical descriptions of fields. Michael Faraday's work on electricity and magnetism introduced the crucial concept of field lines in visible curves through space indicating the direction and strength of forces. Though Faraday worked primarily with electromagnetic fields, his visualization techniques proved equally valuable for understanding gravitational fields. Faraday imagined field lines emanating from masses like electric field lines emanated from charges. The density of field lines indicated field strength, and their direction showed which way a test mass would accelerate. This picture made the abstract mathematical field concept more intuitive, though it didn't explain how the field actually exerted forces. The Scottish physicist James Clerk Maxwell, building on Faraday's ideas, developed a complete mathematical theory of electromagnetic fields in the 1860s. Maxwell's equations showed that electric and magnetic fields could propagate through space as waves travelling at the speed of light. This raised an obvious question. Might gravity also propagate as waves at finite speed despite Laplace's stability arguments? Maxwell himself attempted to create a mechanical model of the gravitational field using spinning vortices in an elastic ether. He imagined space filled with tiny spinning cells that could transmit forces through their interactions. While this model failed to accurately describe gravity, it represented a serious attempt to provide a mechanical foundation for action at a distance. The concept of gravitational potential energy became increasingly important in the late 19th century. Physicists recognized that lifting a mass against gravity stored energy in the gravitational field itself. This energy wasn't located in the mass or in Earth, but somehow distributed through the space between them. The field had become a physical entity capable of storing and transmitting energy. Lord Kelvin calculated the gravitational potential energy of the solar system and used it to estimate the sun's age. He reasoned that if the sun was slowly contracting under its own gravity, the released potential energy could power its luminosity. His calculation gave an age of only 20 million years, far too short for geological and biological evolution. This Kelvin problem wouldn't be resolved until nuclear fusion was discovered in the 20th century. The French mathematician Henri Poincaré made crucial contributions to understanding gravitational dynamics in complex systems. His work on the three-body problem showed that even in Newton's deterministic universe, the motion of three gravitationally interacting bodies could be chaotic and unpredictable over long periods. Small changes in initial conditions led to vastly different outcomes, a phenomenon now called sensitive dependence on initial conditions. Poincaré's work revealed that the clockwork universe of Laplace, where perfect knowledge of present conditions allowed prediction of all future states, was an illusion even in classical mechanics. Gravitational interactions in systems with more than two bodies created intrinsic unpredictability. The solar system might be stable, but its detailed future state couldn't be calculated arbitrarily far in advance. The search for a mechanical explanation of gravity led to increasingly exotic proposals. Some physicists suggested that gravity resulted from shadowing effects in a sea of ultramundane corpuscles bombarding all objects from all directions. Objects shadowed each other from these impacts, creating an apparent attractive force. Others proposed that gravity arose from pressure differences in the ether or from electromagnetic interactions at subatomic scales. The Lesage theory of gravitation, developed by Georges-Louis Lesage in the 18th century and refined by others in the 19th, proposed that space was filled with tiny particles moving at high speed in all directions. Material bodies absorbed or slowed these particles, creating shadows. Two bodies would shield each other from impacts on their facing sides, causing them to be pushed together by unbalanced impacts on their opposite sides. While ingenious mechanical theories of gravity faced insurmountable problems, they typically predicted that planetary motion would decay due to drag from the gravitational medium. They couldn't explain why gravitational and inertial mass were identical. They required ad hoc assumptions about the properties of hypothetical particles or ethers. None successfully reproduced all the predictions of Newton's simple inverse square law. By the end of the 19th century, physicists had developed powerful mathematical tools for working with gravitational fields, but remained puzzled by their physical nature. The field concept had proven invaluable for calculations and visualization, but whether fields were real physical entities or merely mathematical conveniences remained unclear. The gravitational field carried energy and momentum, suggesting physical reality. Tidal effects showed that the field had local properties not determined solely by distant sources. The field mediated forces between masses, somehow transmitting information about their positions and motions. Yet no one could explain how empty space accomplished these feats. The stage was set for a revolutionary reconceptualization of gravity. The tools developed to understand fields differential geometry, tensor calculus, field equations would prove essential for Einstein's general relativity. The philosophical questions raised by action at a distance would motivate the search for a new understanding of space and time themselves. The 19th century's careful mathematical exploration of gravitational fields, even without understanding their physical nature, laid groundwork for 20th century breakthroughs. Physicists had learned to work with fields as abstract mathematical entities, to calculate their properties and effects without requiring mechanical models. This mathematical sophistication would prove crucial when Einstein showed that gravity wasn't a force at all, but the curvature of spacetime itself. In a small apartment in Bern, Switzerland, a 26-year-old patent clerk was having what he would later call the happiest thought of my life. Albert Einstein imagined a person falling from a roof and realized that during the fall the person would feel weightless. In that moment of free fall, gravity effectively disappears. This simple observation would lead to the most profound reconceptualization of gravity since Newton, transforming our understanding of space, time, and the cosmos itself. Einstein's journey toward general relativity began with a puzzle that emerged from his special theory of relativity, published in 1905. Special relativity had shown that space and time were intertwined, that simultaneity was relative, and that nothing could travel faster than light. But Newton's gravity acted instantaneously across any distance, incompatible with the speed limit Einstein had discovered. If the sun suddenly vanished, Newton's theory said Earth would immediately fly off in a straight line. But special relativity insisted that no information could travel faster than light. The principle of equivalence inspired by that thought of the falling person became Einstein's key insight. In a small enough region of space, the effects of gravity are indistinguishable from acceleration. A person in a windowless elevator can't tell whether they're being pulled down by Earth's gravity or pushed up by an accelerating elevator in deep space. Similarly, a freely falling observer experiences no gravitational force. They're in an inertial reference frame, just like an observer floating in deep space. This equivalence between gravity and acceleration had profound implications. If gravity could be transformed away by choosing the right reference frame, then perhaps gravity wasn't a force at all, but something more fundamental about the nature of space-time itself. Einstein spent 8 years from 1907 to 1915 developing this insight into a complete theory. The mathematics Einstein needed didn't exist in physics textbooks. He had to learn differential geometry, developed by mathematicians like Bernhard Riemann and Tullio Levi-Civita, to study curved spaces in abstract mathematical terms. Einstein's friend, Marcel Grossmann, a mathematician, helped him navigate this unfamiliar mathematical landscape. Together, they explored how to describe curved four-dimensional spacetime and how matter and energy might cause such curvature. Riemann had shown in the mid-19th century that curved spaces could be described intrinsically, without reference to any higher dimensional flat space in which they might be embedded. A two-dimensional being on a sphere's surface could discover its curvature by measuring triangles and finding their angles summed to more than 180 degrees. Similarly, we could discover spacetime curvature through local measurements without needing to visualize four-dimensional curves. The concept of curved spacetime was revolutionary and difficult to grasp. In Newton's universe, space was a fixed stage on which matter moved according to gravitational forces. In Einstein's universe, matter and energy told spacetime how to curve, and curved spacetime told matter how to move. Gravity wasn't a force pulling objects together, but the result of objects following the straightest possible paths through curved spacetime. Einstein's field equations, finally completed in November 1915, were deceptively simple in form, but staggeringly complex in implication. Written in tensor notation, they stated that the curvature of spacetime at any point equals the energy and momentum density at that point multiplied by a constant involving Newton's gravitational constant and the speed of light. 10 coupled nonlinear partial differential equations encoded how matter and energy warped the fabric of reality itself. The mathematical beauty of general relativity was breathtaking. The theory satisfied the principle of general covariance. The laws of physics took the same form in all coordinate systems, not just inertial ones, as in special relativity. This meant there were no privileged reference frames, no absolute space or time. The universe had no fixed backdrop. Space-time itself was dynamic, capable of bending, stretching, and rippling. To visualize curved space-time, physicists often use the rubber sheet analogy. Imagine space-time as a stretched rubber sheet. Place a bowling ball on it, and the sheet curves downward. Roll a marble nearby, and it curves toward the bowling ball, not because of an attractive force, but because it's following the straightest path on the curved surface. While this analogy has limitations, it shows only two spatial dimensions and requires gravity to create the depression. It captures the essential idea that mass curves space-time and objects move along geodesics in that curved space-time. Einstein's theory made precise testable predictions that differed from Newton's. The orbit of Mercury, which had puzzled astronomers for decades, provided the first confirmation. Newton's theory predicted that Mercury's elliptical orbit should precess due to gravitational tugs from other planets. But observations showed an extra 43 arc-seconds per century of precession. General relativity predicted exactly this extra precession due to the curvature of spacetime near the Sun. The bending of starlight by the Sun provided even more dramatic confirmation. Einstein predicted that spacetime curvature around massive objects would bend light paths, causing stars near the Sun to appear displaced from their true positions. During the 1919 solar eclipse, Arthur Eddington led expeditions to measure star positions near the darkened Sun. The results, matching Einstein's predictions, made headlines worldwide and transformed Einstein into a celebrity. Gravitational time dilation, another prediction of general relativity, stated that clocks run slower in stronger gravitational fields. Time itself flows differently, depending on spacetime curvature. A clock at sea level runs slower than one on a mountaintop, though the effect is tiny for Earth's weak gravity. Near a black hole, time dilation becomes extreme. An outside observer could watch someone falling into a black hole appear to slow down and freeze at the event's horizon. The Global Positioning System provides daily confirmation of gravitational time dilation. GPS satellites orbit at 20,000 kilometers altitude, where Earth's gravitational field is weaker than at the surface. Their clocks run about 45 microseconds per day, faster than Earth-based clocks, due to gravitational time dilation, partially offset by special relativistic effects from their orbital motion. Without correcting for these relativistic effects, GPS would accumulate positioning errors of about 10 kilometers per day. General relativity revealed that the universe itself could be dynamic. Einstein initially added a cosmological constant to his equations to maintain a static universe, calling it later his greatest blunder, when Edwin Hubble discovered cosmic expansion. The equations naturally described an expanding or contracting universe, predicting what we now call the Big Banger moment, when all spacetime emerged from a singularity of infinite density and curvature. Black holes emerged as perhaps the most exotic prediction of general relativity. Karl Schwarzschild found the first exact solution to Einstein's equations in 1916, describing spacetime around a spherical mass. His solution showed that if mass were compressed within a critical radius, now called the Schwarzschild radius, spacetime curvature would become so extreme that nothing, not even light, could escape. The boundary of no return, the event horizon, marked a region where spacetime curved back on itself. Initially, black holes seemed like mathematical curiosities rather than physical possibilities. Even Einstein doubted they could actually form in nature. But in the 1930s, Subrahmanyan Chandrasekhar showed that stellar remnants above a certain mass would collapse indefinitely under their own gravity. J. Robert Oppenheimer and Hartland Snyder demonstrated in 1939 that such collapse would indeed create black holes as described by general relativity. The geometry of spacetime around rotating masses proved even more interesting. In 1963, Roy Kerr found solutions describing rotating black holes, which drag spacetime around with them in a phenomenon called frame dragging. Near a rotating black hole, spacetime itself rotates, and nothing can remain stationary relative to distant stars. This effect, though much weaker occurs around any rotating mass, including Earth, and has been measured by satellite experiments. Gravitational lensing, where massive objects bend light from distant sources, became a powerful astronomical tool. Fritz Zwicky predicted in 1937 that galaxy clusters could act as gravitational lenses, magnifying and distorting images of more distant galaxies. These cosmic lenses now allow astronomers to study the early universe, map dark matter distribution, and discover planets orbiting distant stars through microlensing events. The expansion of the universe itself represented one of general relativity's most profound predictions. Alexander Friedmann and Georges Lemaitre independently showed that Einstein's equations naturally described an expanding universe emerging from an initial singularity. The cosmic microwave background radiation, discovered in 1964, provided stunning confirmation of this Big Bang model, showing the universe's baby picture from when it first became transparent to light 380,000 years after the beginning. Wormholes, hypothetical shortcuts through spacetime, emerged from general relativity's mathematics. Einstein and Nathan Rosen showed in 1935 that the equations allowed bridges connecting distant regions of spacetime or even different universes. While probably not naturally occurring and requiring exotic matter to stay open, wormholes captured imaginations and demonstrated the strange possibilities lurking in Einstein's equations. The unification of space and time into spacetime had philosophical implications as profound as the scientific ones. Past, present, and future became different slices through a four-dimensional spacetime manifold. The block universe interpretation suggested that all moments exist eternally in spacetime, with our consciousness experiencing them sequentially. Free will, causality, and the nature of time itself required reconsideration in this new framework. General relativity changed how we understand the cosmos at every scale. The universe became a dynamic, evolving entity rather than a static container. Space and time lost their absolute character, becoming aspects of a unified spacetime shaped by matter and energy. Gravity transformed from a mysterious force into the geometry of spacetime itself, no more requiring explanation than the statement that parallel lines converge on a sphere's surface. Yet general relativity raised new mysteries even as it solved old ones. The theory predicted its own breakdown at singularities, points of infinite density and curvature, where the equations became meaningless. The centers of black holes and the universe's beginning represented boundaries of scientific knowledge, places where quantum effects presumably became important, but no quantum theory of gravity existed. The relationship between general relativity and quantum mechanics became physics' central challenge. General relativity described gravity and the large-scale universe with exquisite precision. Quantum mechanics described particles and forces at the smallest scales with equal success. But the two theories seemed fundamentally incompatible, using different mathematics and making contradictory assumptions about the nature of spacetime. Einstein spent his last decade searching unsuccessfully for a unified field theory, combining gravity with electromagnetism. He couldn't accept quantum mechanics' probabilistic nature, believing that a deeper deterministic theory must exist. His famous assertion that God does not play dice reflected his conviction that the universe operated according to elegant deterministic laws, even if we hadn't yet discovered them. Modern measurements continue confirming general relativity's predictions with ever greater precision. Gravitational lensing maps dark matter throughout the universe. Binary pulsars lose energy exactly as predicted by gravitational wave emission. Atomic clocks verify gravitational time dilation to parts per billion. Frame dragging around Earth has been measured by satellite gyroscopes. No deviation from Einstein's century-old theory has been found despite increasingly sensitive tests. The cosmos reveals gravity's artistry on scales that dwarf human comprehension. From the delicate dance of binary stars to the majestic spiral arms of galaxies, from the violent collisions of galaxy clusters to the vast cosmic web spanning billions of light years, gravity shapes every structure we observe in the universe. Each scale tells its own story of how this fundamental force creates order from chaos, builds complexity from simplicity, and drives the cosmic evolution that eventually produced stars, planets, and life itself. In our own solar system, gravity orchestrates a complex ballet that has continued for 4.5 billion years. The Sun, containing 99.86% of the solar system's mass, dominates the gravitational landscape. Its immense gravity holds 8 planets, dozens of moons, thousands of asteroids, and trillions of comets in bound orbits. Yet each object also pulls on every other, creating a rich tapestry of gravitational interactions that shape orbital evolution over millions of years. The planets follow elliptical orbits, as Kepler discovered. But these ellipses aren't fixed in space. Gravitational perturbations from other planets cause orbital elements to change slowly over time. Mercury's perihelion advances, Mars's eccentricity varies, Earth's axis precesses. These secular changes accumulate over geological timescales, affecting planetary climates and potentially influencing the development and evolution of life. Jupiter, the solar system's gravitational giant after the Sun, profoundly influences the entire system's architecture. Its gravity shepherds the asteroid belt, creating gaps called Kirkwood gaps, where orbital resonances with Jupiter destabilize asteroid orbits. The Trojan asteroids cluster at Jupiter's Lagrange points, positions where the combined gravity of Jupiter and the Sun creates stable gravitational wells. Jupiter's gravity also deflects many comets that might otherwise impact inner planets, earning it the title vacuum cleaner of the solar system. The NICE model, developed in the early 2000s, suggests that the giant planets formed closer together and migrated to their current positions through gravitational interactions with a disk of planetesimals. This migration explains many puzzling features of the solar system. The late heavy bombardment that scarred the Moon 3.9 billion years ago, the current orbital spacing of the giant planets, and the distribution of Kuiper Belt objects beyond Neptune. Tidal forces arising from differential gravity across extended objects sculpt moons and planets throughout the solar system. Earth's moon raises tides in our oceans, but Earth simultaneously raises much stronger tides in the moon's solid body. These tidal forces long ago slowed the moon's rotation until it became tidally locked, always showing the same face to Earth. The same process is gradually slowing Earth's rotation, lengthening our days by about 1.7 milliseconds per century. Io, Jupiter's innermost large moon, experiences extreme tidal heating from Jupiter's gravity combined with gravitational tugs from Europa and Ganymede. These tidal forces knead Io's interior like bread dough, generating heat that powers the most volcanically active body in the solar system. Europa's subsurface ocean, kept liquid by tidal heating beneath its icy crust, represents one of the most promising places to search for extraterrestrial life. Saturn's rings provide a natural laboratory for studying gravitational dynamics. The rings consist of countless ice particles, each following its own orbit around Saturn. Gravitational resonances with Saturn's moons create gaps and sharp edges in the rings. Shepherd moons use their gravity to confine narrow rings, while spiral density waves propagate through the rings like sound waves through air. The ring's intricate structure reveals gravity operating on scales from individual particles to the entire ring system. Binary star systems, where two stars orbit their common center of mass, comprise about half of all star systems. These gravitationally bound pairs exhibit remarkable diversity. Some binaries orbit so closely that they share stellar atmospheres, transferring mass between them. Others are separated by thousands of astronomical units, taking millions of years to complete one orbit. The gravitational dynamics of binary systems can be surprisingly complex, especially when the stars have comparable masses. Mass transfer in close binary systems drives some of the universe's most energetic phenomena. When a white dwarf in a binary system pulls matter from its companion star, the accumulated material can trigger a thermonuclear explosion, a nova. If the white dwarf accumulates enough mass to exceed the Chandrasekhar limit of about 1.4 solar masses, it undergoes catastrophic collapse and explosion as a Type Ia supernova, briefly outshining an entire galaxy. Neutron star binaries represent extreme gravitational laboratories. Two neutron stars, each containing more mass than the Sun compressed into a sphere just 20 kilometers across, can orbit each other hundreds of times per second. The Hulse-Taylor binary pulsar, discovered in 1974, provided the first indirect evidence for gravitational waves. Its orbital period decreases by 76 microseconds per year, exactly as predicted by energy loss through gravitational wave emission. Globular clusters, spherical collections of hundreds of thousands of stars, bound by their mutual gravity, are among the oldest structures in the universe. Within these dense stellar cities, gravitational interactions between stars are common. Stars can be ejected from the cluster entirely, form exotic binary systems, or spiral toward the cluster's center. The dynamics of globular clusters can only be understood through complex n-body simulations, tracking the gravitational interactions of every star. Galaxies themselves are vast gravitational systems containing hundreds of billions of stars, along with gas, dust, and dark matter. The Milky Way's spiral arms aren't material structures, but density waves propagating through the galactic disk. As gas and stars pass through these density waves, the increased gravity triggers star formation, creating the bright spiral patterns we observe. The spiral pattern rotates at a different rate than the stars and gas, like a cosmic traffic jam that maintains its structure while individual cars pass through. Our galaxy's gravitational influence extends far beyond its visible stars. The Milky Way is surrounded by a halo of dark matter, extending hundreds of thousands of light years. This invisible mass dominates the galaxy's total gravity, determining orbital velocities in the outer disk and holding satellite galaxies in bound orbits. Without dark matter's gravity, the Milky Way would fly apart. The visible stars alone don't provide enough gravity to hold the galaxy together at observed rotation speeds. The local group, our galactic neighborhood, contains over 80 known galaxies bound together by gravity. The Milky Way and Andromeda, the two largest members, dominate the group's dynamics. Currently separated by 2.5 million light-years, they're approaching each other at about 110 kilometers per second. In approximately 4.5 billion years, they'll collide and merge in a cosmic dance lasting billions of years, eventually forming a single elliptical galaxy. Galaxy collisions, despite their violent appearance, rarely involve direct stellar collisions. The spaces between stars are too vast. Instead, the galaxy's gravitational fields distort each other, creating tidal tails stretching hundreds of thousands of light years. Gas clouds collide and compress, triggering massive bursts of star formation. Supermassive black holes at galactic centers spiral toward each other, eventually merging in events that send gravitational waves rippling across the universe. Galaxy clusters, containing hundreds or thousands of galaxies, are the largest gravitationally bound structures in the universe. The Coma cluster, containing over 1,000 galaxies, spans millions of light years. Within clusters, galaxies orbit at speeds of hundreds of kilometers per second. Hot gas between galaxies, heated to millions of degrees by gravitational compression, emits X-rays that reveal the cluster's total mass distribution. Fritz Zwicky's observations of galaxy clusters in the 1930s provided the first evidence for dark matter. He measured galaxy velocities in the Coma cluster and found they moved too fast to be held by the gravity of visible matter alone. Something invisible outweighing visible matter by a factor of 6 provided the extra gravity needed to hold the cluster together. This missing mass problem would perplex astronomers for decades. Gravitational lensing by galaxy clusters creates some of the most spectacular cosmic images. Massive clusters bend light from background galaxies, creating multiple images, arcs and rings. The cluster Abel 1689 acts as a natural telescope, magnifying galaxies from the early universe that would otherwise be too faint to observe. By analysing lensing patterns, astronomers map the distribution of dark matter throughout clusters, revealing that dark matter and visible matter sometimes separate during cluster collisions. The Bullet cluster provides striking evidence for dark matter's existence. This system consists of two galaxy clusters that collided 150 million years ago. X-ray observations show that hot gas, comprising most of the visible matter, was stripped and shocked during the collision. But gravitational lensing reveals that most of the mass, the dark matter, passed through the collision unaffected. This separation of dark and visible matter cannot be explained by modified theories of gravity alone. Superclusters, collections of galaxy clusters spanning hundreds of millions of light years, form the largest coherent structures in the universe. The Laniakea supercluster, containing our local group and about 100,000 other galaxies, stretches 520 million light-years across. Within superclusters, galaxy clusters and groups move along gravitational flows toward regions of higher density, like water flowing toward valleys in a cosmic landscape. The Great Attractor, a gravitational anomaly in the direction of the Centaurus and Norma constellations, pulls galaxies toward it from hundreds of millions of light-years away. Hidden behind the Milky Way's disk, this massive concentration of matter affects the motion of galaxies throughout our cosmic neighbourhood. The nature of the Great Attractor remained mysterious for decades, until X-ray observations revealed it to be a massive cluster of galaxies previously hidden by dust and stars. The cosmic web, the largest structure in the universe, consists of galaxy filaments separated by vast voids. This web-like pattern emerged from tiny density fluctuations in the early universe, amplified by gravity over billions of years. Dark matter formed the scaffolding, its gravity pulling ordinary matter into filaments where galaxies could form. Computer simulations of structure formation, incorporating gravity and cosmic expansion, reproduce the observed web with remarkable accuracy. Voids, regions nearly empty of galaxies, comprise most of the universe's volume. The Boötes supervoid, spanning 330 million light-years, contains only a few dozen galaxies where thousands would be expected. These cosmic deserts formed as gravity drew matter away toward denser regions. Even in voids, gravity's influence continues. The few galaxies within voids tend to align along tenuous filaments, following the underlying dark matter distribution. The integrated Sachs-Wolf effect demonstrates how cosmic structures affect even light-crossing empty space. Photons from the cosmic microwave background gain energy falling into gravitational wells of superclusters and lose energy climbing out. In our accelerating universe, structures grow while light travels through them, creating a net energy change that provides another probe of cosmic gravity. Gravitational instability drive structure formation at all scales. Tiny quantum fluctuations in the infant universe, stretched to cosmic scales by inflation, seeded all structure we observe today. Regions slightly denser than average attracted surrounding matter through gravity, growing denser still. This runaway process, operating over billions of years, transformed near-uniform gas into the rich tapestry of stars, galaxies, and clusters we observe. Dark energy, discovered through observations of distant supernova, opposes gravity on cosmic scales. This mysterious energy, comprising about 68% of the universe's energy density, causes cosmic expansion to accelerate. While gravity dominates within galaxies and clusters, dark energy wins on larger scales, driving galaxies apart at ever-increasing speeds. The competition between gravity's attraction and dark energy's repulsion will determine the universe's ultimate fate. The future of cosmic structures depends on this cosmic tug-of-war. If dark energy remains constant, gravity will continue forming structures within galaxy clusters while dark energy drives clusters apart. Eventually, billions of years hence, each gravitationally bound cluster will become an island universe, isolated from all others by the accelerating expansion of space. The night sky will gradually empty as distant galaxies disappear beyond our cosmic horizon. In the heart of our galaxy, 26,000 light-years from Earth, lurks a monster. Sagittarius A, a supermassive black hole containing 4 million times the Sun's mass, anchors the Milky Way's centre. Stars whip around it at speeds exceeding 5,000 kilometers per second, their orbits traced over decades of patient observation. This gravitational behemoth, compressed into a region smaller than Mercury's orbit, represents gravity pushed to its absolute limit, a place where spacetime curvature becomes so extreme that our usual concepts of space and time break down entirely. Black holes are gravity's ultimate victory, regions where matter has collapsed so completely that nothing, not even light travelling at 300,000 kilometers per second, can escape. They represent the most extreme gravitational environments in the universe, natural laboratories where Einstein's general relativity confronts the quantum realm, and where the familiar laws of physics stretch to their breaking points and beyond. The journey to understanding black holes began long before Einstein, with a prescient insight by John Michell in 1783. This English clergyman and natural philosopher imagined a star so massive and compact that its escape velocity would exceed the speed of light. Using Newton's laws, he calculated that a star with the Sun's density but 500 times its diameter would trap light entirely. Michel called these hypothetical objects dark stars, anticipating black holes by more than a century. Pierre-Simon Laplace independently reached similar conclusions in 1796, including a brief discussion of dark stars in his treatise on celestial mechanics. But without understanding light's true nature or gravity's relationship to spacetime, these Newtonian dark stars remained philosophical curiosities. The concept disappeared from scientific discourse for over a century, awaiting the revolutionary insights of general relativity. Carl Schwarzschild provided the first exact solution to Einstein's field equations in 1916, while serving on the Russian front during World War I. His solution described the space-time geometry around a spherical, non-rotating mass. Remarkably, this solution showed that if mass were compressed within a critical radius, now called the Schwarzschild radius spacetime curvature, would become infinite at the centre, creating what we now call a singularity. The Schwarzschild radius defines a black hole's point of no return, the event horizon. For a black hole with the Sun's mass, this radius is about 3 kilometres. For Earth, it's just 9 millimetres. The event horizon isn't a physical surface, but a boundary in spacetime. An observer falling through it would notice nothing special at that moment, but they would have passed a point from which no signal could ever reach the outside universe. Initially, physicists viewed the Schwarzschild solution's singularity as a mathematical artifact rather than a physical possibility. Even Einstein believed that nature would prevent such extreme collapse. In 1939, he published a paper attempting to prove that black holes couldn't form, arguing that rotating matter would fling itself apart before reaching the critical density. But that same year, Robert Oppenheimer and Hartland Snyder demonstrated theoretically that sufficiently massive stars would indeed collapse into black holes. The term black hole wasn't coined until 1967 by physicist John Wheeler, who sought a more memorable name than gravitationally completely collapsed object. The name captured both the object's defining characteristic nothing escapes, making it black, and the sense of a hole in spacetime itself. Wheeler's evocative terminology helped bring black holes from mathematical abstraction into mainstream scientific and popular consciousness. Stellar mass black holes form when massive stars exhaust their nuclear fuel and can no longer support themselves against gravity. Stars more than about 20 times the Sun's mass undergo catastrophic collapse when fusion ceases in their cores. Within seconds, the core collapses from thousands of kilometers across to just dozens, then continues collapsing past the point where any known force could halt it. The outer layers explode as a supernova, briefly outshining an entire galaxy, while the core disappears behind an event horizon. During this collapse, matter reaches densities beyond comprehension. A teaspoon of neutron star material weighs as much as Mount Everest, but black hole formation involves densities that make even neutron stars seem gossamer light. The matter doesn't just become dense according to general relativity, it collapses to a point of infinite density, a singularity where our physics equations produce infinities and lose their meaning. The event horizon surrounding this singularity acts as a one-way membrane in spacetime. Its size depends only on the black hole's mass double the mass, double the radius. For a 3 solar mass black hole, typical of stellar collapse, the event horizon spans about 18 kilometers. This seems small, but it encloses a region where spacetime curvature becomes so extreme that space and time effectively exchange roles. Inside the event horizon, the singularity isn't just a place you could avoid visiting, it becomes your inevitable future. Just as you cannot avoid moving forward in time outside a black hole, inside the event horizon, you cannot avoid moving toward the singularity. The radial direction becomes time-like, making movement away from the center as impossible as traveling backward in time. Every path, every possible trajectory leads inexorably to the singularity. Time dilation near black holes creates surreal effects. As you approach the event horizon, time passes increasingly slowly relative to the outside universe. To a distant observer watching you fall in, your clock would appear to slow down, your movements becoming sluggish, your final moments before crossing the horizon stretched to infinity. You would appear to freeze at the horizon, your image redshifting to invisibility, though from your perspective you would pass through normally. This time, dilation isn't just theoretical, it has observable consequences. X-rays from matter spiraling into black holes show characteristic flickering patterns. As the emitting material approaches the event horizon, its orbital period increases due to time dilation, creating a lowest observable frequency that reveals the black hole's mass and spin. These quasi-periodic oscillations provide a direct probe of spacetime in the strong gravity regime. Rotating black holes, described by Roy Kerr's 1963 solution to Einstein's equations are even stranger than their non-rotating counterparts. Real astrophysical black holes rotate because they form from rotating stars that spin faster as they collapse, like figure skaters pulling in their arms. The Kerr solution reveals that rotating black holes drag spacetime around with them, creating a region called the ergosphere, where nothing can remain stationary relative to distant stars. The ergosphere extends beyond the event horizon, creating a region where strange energy extraction is theoretically possible. Roger Penrose showed in 1969 that objects entering the ergosphere could split, with one piece falling into the black hole, while the other escapes with more energy than the original object possessed. This Penrose process extracts rotational energy from the black hole itself, slowing its spin while powering the escaping matter. Frame dragging near rotating black holes twists in falling matter into complex patterns. Magnetic field lines threading the ergosphere can extract enormous amounts of energy, potentially powering the spectacular jets observed from quasars and active galactic nuclei. These jets, sometimes extending millions of light years, represent gravity indirectly powering the most energetic continuous phenomena in the universe. Supermassive black holes, millions to billions of times the Sun's mass, lurk at the centres of most galaxies. Their formation remains mysterious. They might have grown from smaller seed black holes in the early universe, or formed directly from collapsing gas clouds before the first stars. What's certain is their profound influence on galactic evolution. The mass of a galaxy's central black hole correlates tightly with properties of the galactic bulge, suggesting an intimate connection between black hole growth and galaxy formation. The supermassive black hole in galaxy M87, weighing 6.5 billion solar masses, became the first black hole ever directly imaged. In 2019, the Event Horizon Telescope, a planet-sized array of radio telescopes, captured the black hole's shadow, a dark region where light cannot escape, surrounded by a bright ring of superheated matter spiraling inward. This image, showing structure on scales of just a few light hours, confirmed predictions from general relativity with stunning precision. Sagittarius A, our galaxy's central black hole, provides an even closer laboratory for studying extreme gravity. Stars orbiting it have been tracked for decades, their elliptical paths precisely matching predictions from general relativity. The star S2 passes within 17 light hours of the black hole, reaching speeds of 7,650 kilometers per second, 2.5% of light speed. Observations of S2's orbit have confirmed gravitational redshift and orbital precession exactly as Einstein predicted. The thermodynamics of black holes reveals deep connections between gravity, quantum mechanics, and information. In 1973, Jacob Bekenstein proposed that black holes have entropy proportional to their surface area, not their volume. This was revolutionary. Entropy usually scales with volume, as it counts internal microscopic states. But for black holes, all information seems encoded on the two-dimensional event horizon. Stephen Hawking's 1974 discovery that black holes emit radiation transformed our understanding of these objects. By applying quantum field theory to curved spacetime near the event horizon, Hawking showed that particle-antiparticle pairs created from vacuum fluctuations could separate, with one falling in while the other escapes. This Hawking radiation gives black holes a temperature inversely proportional to their mass. The smaller the black hole, the hotter it glows. Hawking radiation implies that black holes slowly evaporate, losing mass and shrinking over vast timescales. A solar mass black hole would take 10 to 67 years to evaporate completely, far longer than the current age of the universe. But microscopic black holes, if they exist, would evaporate rapidly in explosive bursts of radiation. The final moments of black hole evaporation remain mysterious, potentially requiring a quantum theory of gravity to understand. The information paradox arising from Hawking radiation challenges our understanding of quantum mechanics. Information falling into a black hole seems destroyed when the black hole evaporates, violating quantum mechanics' requirement that information be preserved. Various proposed solutions, including firewalls at the horizon, complementarity principles, and holographic descriptions, remain hotly debated, representing one of theoretical physics' deepest puzzles. Black hole mergers, when two black holes spiral together and coalesce, release tremendous amounts of energy as gravitational waves. The first detection of such a merger by LIGO in 2015 opened an entirely new window on the universe. The two black holes, about 30 solar masses each, release 3 solar masses worth of energy in gravitational waves during their final fraction of a second, briefly outshining all the stars in the observable universe combined, though only in gravitational rather than electromagnetic radiation. The ring-down phase after black holes merge provides a unique test of general relativity. The merged black hole vibrates like a struck bell, emitting gravitational waves at characteristic frequencies determined by its mass and spin. These quasi-normal modes match precisely with calculations from perturbation theory in general relativity, confirming that the merger product is indeed a Kerr black hole, as theory predicts. Primordial black holes, hypothetically formed in the early universe from extreme density fluctuations, could range from microscopic to supermassive. If they exist, tiny primordial black holes might constitute some or all of dark matter. Searches for primordial black holes use various techniques, from gravitational microlensing to looking for Hawking radiation from evaporating microscopic black holes, though none have been definitively detected. Intermediate mass black holes, hundreds to thousands of times the Sun's mass, remain elusive. They should form from the first generation of massive stars or in dense star clusters, bridging the gap between stellar and supermassive black holes. Recent gravitational wave observations have detected mergers involving intermediate mass black holes, confirming their existence and providing clues about their formation. The cosmic censorship hypothesis, proposed by Roger Penrose, suggests that singularities are always hidden behind event horizons, never naked and visible to outside observers. This remains unproven but seems necessary for the universe to remain predictable. A naked singularity would be a region where physics breaks down visibly, potentially affecting the entire future light cone in unpredictable ways. Black holes in higher dimensions, studied theoretically in string theory and other approaches to quantum gravity, exhibit even stranger properties. They can have non-spherical event horizons, form black rings and black strings, and undergo instabilities impossible in 4 dimensions. These exotic solutions might seem purely mathematical, but they provide insights into quantum gravity and the fundamental nature of spacetime. Extremal black holes, with maximum possible spin or charge for their mass, hover at the edge of physical possibility. Their event horizons nearly disappear, approaching zero temperature and infinite time dilation. Some theories suggest extremal black holes might provide windows into quantum gravity, as their near-horizon regions exhibit enhanced symmetries that simplify calculations. The firewall paradox, proposed in 2012, suggests that quantum effects might create a wall of high-energy particles at the event horizon, destroying anything that attempts to cross. This would violate general relativity's equivalence principle, which says falling through the horizon should be unremarkable. The debate over firewalls continues, highlighting tensions between general relativity and quantum mechanics. Wormholes, hypothetical shortcuts through spacetime, could theoretically connect black holes to distant regions or other universes. While allowed by general relativity's equations, traversable wormholes would require exotic matter with negative energy density to remain open. No evidence for wormholes exists, but their theoretical study illuminates the boundaries of what spacetime geometry permits. The holographic principle, inspired by black hole thermodynamics, suggests that all information in a volume of space can be encoded on its boundary. This radical idea implies that our three-dimensional world might be a projection of information stored on a distant two-dimensional surface. Black holes, where this principle first emerged, continue driving revolutionary ideas about the nature of reality. Black holes represent gravity's triumph and mystery simultaneously. They're laboratories where general relativity has been tested and confirmed in the strong field regime. Yet they're also places where our physics breaks down, demanding a quantum theory of gravity we don't yet possess. They're invisible, yet shape entire galaxies, destroy information, yet preserve it holographically, exist throughout the universe, yet challenge our understanding of existence itself. For one brief moment on September 14, 2015, at 5:51 a.m. Eastern Daylight Time, the length of a 4-kilometer tunnel in Louisiana stretched by a distance smaller than a proton's width, while simultaneously an identical tunnel in Washington state contracted by the same infinitesimal amount. This minute distortion of space itself, lasting less than a quarter second, marked humanity's first direct detection of gravitational waves, ripples, in the fabric of space-time that Einstein had predicted a century earlier but doubted we would ever detect. The waves that swept through Earth that morning had travelled 1.3 billion years from a cosmic catastrophe of unimaginable violence. Two black holes, one 36 times the Sun's mass and the other 29, had spiralled together and merged in a fraction of a second, converting 3 solar masses more mass than exists in all the planets, moons, asteroids, and comets in our solar system combined directly into gravitational wave energy. The space around them writhed and pulsed, sending waves of distorted spacetime racing outward at light speed. Einstein first predicted gravitational waves in 1916, just months after completing general relativity. His equations showed that accelerating masses would create propagating distortions in spacetime, much as accelerating electric charges create electromagnetic waves. But while electromagnetic waves are oscillations of electric and magnetic fields travelling through spacetime, gravitational waves are oscillations of spacetime itself. They stretch and squeeze the very fabric of reality as they pass. The mathematics was clear, but Einstein himself vacillated about whether gravitational waves were real or merely coordinate artifacts. In 1936, he and Nathan Rosen submitted a paper claiming to prove gravitational waves didn't exist, but referee reports pointing out errors led Einstein to reverse his conclusion. The confusion was understandable. Gravitational waves involve subtle concepts about what's physically real versus what depends on coordinate choice in general relativity. The weakness of gravitational waves makes them extraordinarily difficult to detect. Even the strongest astrophysical sources produce waves that stretch and compress space by factors of only 10 to the 21 or smaller by the time they reach Earth. If a gravitational wave stretched the entire distance from Earth to the Sun, the change would be less than the width of a hydrogen atom. This incredible weakness reflects gravity's fundamental feebleness. Compared to other forces, it takes the most extreme events in the universe to produce detectable space-time ripples. Joseph Weber at the University of Maryland built the first gravitational wave detectors in the 1960s. massive aluminum cylinders designed to ring like bells when gravitational waves pass through. Weber claimed detections creating enormous excitement, but other groups couldn't reproduce his results. While Weber's bars weren't sensitive enough to detect real astrophysical sources, his pioneering work launched the experimental field of gravitational wave astronomy. The idea for laser interferometry to detect gravitational waves emerged in the 1970s. By splitting a laser beam and sending it down perpendicular arms, then recombining the beams, tiny changes in arm length would shift the interference pattern. Rainer Weiss at MIT worked out the fundamental noise sources and required sensitivities, showing that kilometre-scale interferometers could potentially detect gravitational waves from cosmic sources. Building detectors sensitive enough required overcoming seemingly impossible challenges: seismic vibrations from earthquakes thousands of miles away, thermal fluctuations in mirrors, quantum fluctuations in laser light, even the gravitational pull of clouds passing overhead, all create noise that can overwhelm gravitational wave signals. The laser interferometer. Gravitational Wave Observatory, LIGO, took decades to develop technologies to suppress these noise sources. LIGO's interferometers are marvels of precision engineering. The mirrors, among the smoothest objects ever created, hang from quadruple pendulum systems to isolate them from ground vibrations. The laser light bounces between the mirrors hundreds of times, effectively lengthening the arms to increase sensitivity. The beam tubes maintain better vacuum than interstellar space to prevent air molecules from scattering the laser light. Active feedback systems correct for Earth's constant motion, keeping the mirrors positioned to nanometer precision. The advanced LIGO detectors that made the first detection can measure distance changes of 10 19 meters, equivalent to measuring the distance to the nearest star to the width of a human hair. This extraordinary sensitivity requires accounting for effects most physicists never consider: the gravitational pull of trucks driving miles away, the quantum radiation pressure from photons bouncing off mirrors, even the Brownian motion of atoms in the mirror coatings. The waveform detected on September 14, 2015, lasted just 200 milliseconds, but encoded remarkable information. As the black holes spiraled inward, the gravitational wave frequency increased from 35 to 250 Hz audible frequencies that LIGO scientists converted to sound, creating the famous chirp of merging black holes. The waveform's shape precisely matched supercomputer simulations of black hole mergers, confirming general relativity's predictions in the strong field regime where spacetime curvature becomes extreme. The detection's significance extends far beyond confirming Einstein's prediction. It opened an entirely new way of observing the universe, comparable to Galileo first pointing a telescope at the sky. Gravitational waves carry information about regions electromagnetic radiation cannot escape: the interiors of supernova, the first fraction of a second after the Big Bang, the event horizons of black holes. They pass through matter essentially unimpeded, bringing us signals from the most violent events in the cosmos. Since that first detection, LIGO and its European partner Virgo have observed dozens of black hole mergers, revealing a previously unknown population of heavy stellar mass black holes. Some mergers involve black holes too massive to form from present-day stars, suggesting they might be second-generation black holes formed from previous mergers or remnants from the early universe, when stars could grow much larger. The merger GW 70817, detected on August 17, 2017, marked another watershed moment, the first observation of gravitational waves from colliding neutron stars. Unlike black hole mergers, neutron star collisions produce electromagnetic radiation across the spectrum. Within seconds of LIGO and Virgo detecting the gravitational waves, the Fermi Space Telescope observed a gamma ray burst from the same location. Over the following weeks, telescopes worldwide observed the event's aftermath in visible light, infrared, ultraviolet, X-rays and radio waves. This multi-messenger observation combining gravitational waves with electromagnetic signals revealed extraordinary details about the collision. The neutron stars, each about 1.4 solar masses, but only 20 kilometers across, orbited each other hundreds of times per second in their final moments. Their collision created temperatures of billions of degrees, pressures exceeding those in atomic nuclei, and conditions that forge heavy elements like gold, platinum, and uranium through rapid neutron capture. The optical and infrared glow from GW170817, called a kilonova, confirmed that neutron star mergers are cosmic foundries for heavy elements. The collision ejected about 0.05 solar masses of material enriched in freshly synthesized elements. Spectroscopic observations identified specific elements being created, solving the long-standing mystery of where elements heavier than iron originate. The gold in jewelry, the uranium in Earth's core, the platinum in catalytic converters, all were forged in ancient neutron star collisions whose gravitational waves once rippled past Earth undetected. Gravitational waves from neutron star mergers also probe the exotic physics of matter at nuclear densities. The waves encode information about the neutron star equation of state how matter behaves when compressed beyond atomic nuclei. As the stars distort each other through tidal forces before merging, their deformability affects the gravitational waveform. These measurements constrain models of quantum chromodynamics at densities unreachable in terrestrial experiments. The speed of gravitational waves provides fundamental tests of physics. The near-simultaneous arrival of gravitational waves and gamma rays from GW170817 after travelling 130 million light-years confirm that gravity propagates at light speed to within 1 part in 10^15. This measurement constrains alternative theories of gravity and confirms a key prediction of general relativity. Continuous gravitational waves, as opposed to the brief chirps from mergers, might come from rapidly rotating neutron stars with slight asymmetries. Mountains just millimeters high on a neutron star's surface would produce continuous gravitational waves as the star rotates hundreds of times per second. While not yet detected, searches for continuous waves could reveal the neutron star population and internal structure. The stochastic gravitational wave background, analogous to the cosmic microwave background, but in gravitational rather than electromagnetic radiation, could preserve information from the universe's first moments. Inflation, the hypothetical exponential expansion in the first 10 to the 32 seconds, would have produced primordial gravitational waves. Unlike electromagnetic radiation, which couldn't propagate until the universe became transparent, 380,000 years after the Big Bang, gravitational waves have travelled freely since the beginning, potentially carrying information about quantum gravity and the universe's birth. Pulsar timing arrays search for gravitational waves at much lower frequencies than LIGO can detect. By precisely monitoring the arrival times of pulses from millisecond pulsars, astronomers can detect the subtle changes caused by passing gravitational waves with periods of years. These experiments are sensitive to supermassive black hole binaries, pairs of billion solar mass black holes orbiting each other in galaxy centres following galactic mergers. The European Space Agency's LISA mission, planned for the 2030s, will detect gravitational waves from space using laser interferometry between spacecraft separated by millions of kilometers. Free from seismic noise and unlimited by Earth's size, LISA will observe lower frequencies than ground-based detectors, revealing mergers of supermassive black holes, extreme mass ratio inspirals, where stellar mass objects spiral into supermassive black holes, and potentially the gravitational wave background from the early universe. Future ground-based detectors, like the Einstein telescope and Cosmic Explorer, will have 10 times LIGO's sensitivity, detecting black hole mergers throughout the observable universe. They'll observe hundreds of thousands of events yearly, mapping black hole populations across cosmic time, testing general relativity with unprecedented precision, and potentially discovering new gravitational wave sources we haven't imagined. Gravitational wave memory effects, permanent distortions of spacetime left after waves pass, offer another observable phenomenon. After a gravitational wave train passes, test masses don't return to their original positions, but remain slightly displaced. This memory effect, while tiny, accumulates from multiple events and could be detected by future instruments, providing information about gravitational wave sources' total energy emission. The detection of gravitational waves has philosophical implications as profound as their scientific importance. These ripples in spacetime confirm that space and time aren't merely the stage on which physics happens, but dynamic participants in cosmic events. Empty space can ripple, stretch, and carry energy across the universe. The substrate of reality itself vibrates with waves from distant catastrophes. Gravitational waves also demonstrate the universe's deep unity. The same equations describing ripples from colliding black holes also govern the gentle pull between Earth and Moon. The mathematics developed for abstract curved spaces applies to real, measurable distortions of space and time. Theory and observation converge with extraordinary precision, validating our mathematical descriptions of nature's most fundamental interactions. At the heart of modern physics lies an uncomfortable truth that keeps theoretical physicists awake at night. Our two most successful theories of nature fundamentally contradict each other. General relativity describes gravity as the smooth continuous curvature of spacetime, a geometric property of the universe itself. Quantum mechanics describes the other three forces: electromagnetism, the strong nuclear force, and the weak nuclear force, in terms of discrete particles exchanged between interacting objects. These two magnificent theories, each verified to extraordinary precision in its domain, become mutually incompatible when we try to combine them into a single framework. The problem isn't merely academic. At the center of every black hole, where matter collapses to infinite density, general relativity predicts a singularity where spacetime curvature becomes infinite and the theory breaks down. In the first 1043 seconds after the Big Bang, when the entire observable universe was compressed into a region smaller than the Planck length, quantum effects and gravity were equally important. Understanding these extreme conditions requires a quantum theory of gravity, yet after nearly a century of effort by many of physics' brightest minds, such a theory remains elusive. The incompatibility between general relativity and quantum mechanics runs deep. In quantum mechanics, the uncertainty principle states that you cannot simultaneously know a particle's exact position and momentum, but general relativity requires spacetime to have definite geometric properties at every point. Quantum mechanics describes fields as operators acting on wave functions in a fixed spacetime background. General relativity says spacetime itself is dynamic, shaped by the matter and energy within it. Quantum mechanics preserves information in principle. You can always reconstruct the past from complete knowledge of the present. Black holes in general relativity appear to destroy information when they evaporate through Hawking radiation. The scale at which quantum gravity becomes important is almost unimaginably small. The Planck length, about 10⁻35 meters, is the scale where quantum uncertainty in position becomes comparable to the Schwarzschild radius of a particle's mass energy. It's smaller than a proton by about the same factor that a proton is smaller than the solar system. The Planck time, how long light takes to travel one Planck length, is 1043 seconds. The Planck energy, the energy of a particle whose Compton wavelength equals its Schwarzschild radius, is about 1019 GeV. Roughly, the energy of a lightning bolt concentrated into a single particle. These extreme scales explain why quantum gravity has proven so difficult to study. The Large Hadron Collider, humanity's most powerful particle accelerator, reaches energies of about 10⁻⁴ GeV, 15 orders of magnitude below the Planck energy. Building an accelerator to directly probe quantum gravity would require a ring the size of the galaxy. Even the most energetic cosmic ray particles fall short by many orders of magnitude. We're trying to understand physics at scales trillion times smaller than anything we can directly probe. String theory represents the most developed approach to quantum gravity, though it remains controversial and unverified. Instead of point particles, string theory proposes that fundamental entities are one-dimensional strings vibrating in 10 or 11 dimensions. Different vibrational modes correspond to different particles. One mode might be an electron, another a quark, another a graviton. Gravity emerges naturally in string theory because one vibrational mode always corresponds to a massless spin 2 particle, which must be the graviton. The extra dimensions in string theory, beyond the 3 spatial and 1 temporal dimension we observe, must be compactified, curled up so small we don't notice them. Imagine an ant walking on a garden hose. To the ant, the hose has 2 dimensions along its length and around its circumference. But from far away, the hose looks one-dimensional. Similarly, string theory suggests our universe has hidden dimensions curled up at every point in space, too small to detect with current technology. String theory's mathematical consistency requires supersymmetry, a proposed symmetry between fermions and matter particles and bosons, force carriers. Every known particle would have a superpartner. Electrons would have selectrons, quarks would have squarks, photons would have photinos. But no superpartners have been observed despite intensive searches. Either supersymmetry is broken at energies higher than we can reach, or string theory needs modification. The landscape problem plagues string theory. The theory allows perhaps 10 to 500 different ways to compactify the extra dimensions, each giving a universe with different physical laws. Which compactification describes our universe? Why this one rather than another? Some physicists embrace the landscape, arguing it explains fine-tuning through anthropic selection. We observe this compactification because others don't allow observers. Critics argue this makes string theory unfalsifiable, more philosophy than science. Loop quantum gravity takes a different approach, attempting to quantize spacetime itself, rather than describing particles moving through spacetime. In this theory, space isn't continuous but made of discrete loops at the Planck scale, like a fabric woven from incredibly tiny threads. These loops form spin networks, graphs where edges carry quantum numbers related to area and nodes represent quantum volumes. Spacetime becomes a spin foam, the 4-dimensional evolution of spin networks. Loop quantum gravity predicts that area and volume are quantized, coming in discrete units like energy in quantum mechanics. The smallest possible area is about the Planck length squared, the smallest volume about the Planck length cubed. This discreteness might resolve singularities instead of collapsing to infinite density, matter would reach a maximum density where quantum geometry effects halt further collapse. Black holes would have no singularities, just regions of maximum curvature. The Big Bounce cosmology emerging from loop quantum gravity suggests our universe's Big Bang wasn't the beginning, but a transition from a previous contracting phase. As the universe contracted, quantum geometry effects would become important before reaching a singularity, causing a bounce that appears as our Big Bang. This cyclic cosmology avoids the initial singularity problem while potentially leaving observable signatures in the cosmic microwave background. Causal set theory proposes that spacetime consists of discrete points with causal relationships, which events can influence which others. The seemingly continuous spacetime we observe emerges from this discrete structure at large scales, like how water seems continuous despite consisting of discrete molecules. The number of points in a region determines its volume, while the causal relationships determine its geometry. This approach naturally incorporates causality, a fundamental aspect of spacetime that other approaches must add by hand. Asymptotic safety suggests gravity might be a perfectly good quantum field theory if treated properly. The idea is that gravity becomes simpler at high energies, with coupling constants flowing to fixed points rather than diverging. This would make quantum gravity well-defined at all scales without requiring new particles or dimensions. While mathematically appealing, proving asymptotic safety requires calculations so complex that definitive results remain elusive. Emergent gravity theories propose that gravity isn't fundamental but emerges from more basic phenomena, like how temperature emerges from molecular motion. Eric Verlinde's entropic gravity suggests gravity results from the tendency of systems to maximize entropy. In this view, what we call gravitational attraction is really the statistical tendency of matter to arrange itself in ways that maximize the information content of spacetime. While intriguing, emergent gravity theories struggle to reproduce all of general relativity's successful predictions. The holographic principle, inspired by black hole thermodynamics, suggests that all information in a volume can be encoded on its boundary. The ADS-CFT correspondence, discovered by Juan Maldacena, provides a concrete realization. Certain gravitational theories in anti-d Sitter space are exactly equivalent to conformal field theories on the boundary. This duality means difficult gravitational calculations can be translated into easier field theory calculations and vice versa. While our universe isn't anti-d Sitter, the correspondence provides valuable insights into quantum gravity. Black hole information paradox remains central to quantum gravity research. When a black hole evaporates through Hawking radiation, what happens to the information that fell in? If it's destroyed, quantum mechanics is violated. If it escapes in the radiation, how does it get out from behind the event horizon? Recent progress suggests information might escape through subtle quantum correlations in the radiation, but the exact mechanism remains mysterious. Experimental tests of quantum gravity seem almost impossible given the Planck scale's inaccessibility, but ingenious proposals exist. Quantum gravity might cause decoherence, making quantum superpositions collapse faster for more massive objects. It might violate Lorentz invariance, causing high-energy photons to travel at slightly different speeds. It might create tiny black holes in cosmic ray collisions or particle accelerators. Gravitational waves from the early universe might carry signatures of quantum gravity effects. The cosmological constant problem represents perhaps the worst prediction in physics history. Quantum field theory predicts vacuum energy density about 10^120 times larger than observed. This discrepancy between quantum mechanics and general relativity is so vast that it suggests fundamental misunderstanding. Various solutions have been proposed: supersymmetry, anthropic selection, vacuum energy, cancellation mechanisms, but none are satisfactory. The quest for quantum gravity has driven mathematical innovations with applications far beyond physics. String theory has advanced algebraic geometry, topology, and number theory. Loop quantum gravity has developed new mathematical tools for dealing with background-independent theories. The holographic principle has connected gravity to quantum information theory. Even failed approaches have enriched our mathematical toolkit. Different approaches to quantum gravity make different predictions about the nature of reality. Is spacetime fundamental or emergent? Are there extra dimensions? Is the universe discrete or continuous at the smallest scales? Is information fundamental? These aren't just technical questions, but profound inquiries into the nature of existence itself. The answer, when we find it, will likely transform our understanding of reality as radically as relativity and quantum mechanics did a century ago. The sociology of quantum gravity research reflects the challenge's difficulty. Communities working on different approaches, string theory, loop quantum gravity, and others, sometimes barely communicate, developing separate languages and conferences. Young physicists face difficult career choices, work on established but possibly wrong approaches, or pursue alternatives that might be revolutionary or might be dead ends. The field's mathematical complexity means few can evaluate all approaches competently. Life on Earth exists in a constant dialogue with gravity, a conversation that began the moment the first organic molecules assembled in primordial waters 4 billion years ago, and continues with every heartbeat, every step, every reaching branch and diving whale. This most fundamental force hasn't merely been a backdrop to evolution, but an active participant, shaping the forms life takes, the strategies organisms employ, and the very limits of what biology can achieve on a world where every living thing must constantly work against the downward pull of one Earth gravity. In the warm, shallow seas where life likely began, gravity's first gift was stratification. Heavier particles settled to the bottom, while lighter ones remained suspended, creating gradients of nutrients and minerals. Thermal differences caused by solar heating at the surface and cooling at depth, maintained by gravity preventing wholesale mixing, established convection currents that transported materials and created diverse microenvironments. These gravitationally organized layers provided the varied conditions necessary for complex chemistry to explore different evolutionary possibilities. The earliest microscopic life forms were largely indifferent to gravity's pull. For single-celled organisms, smaller than a millimeter, viscous forces dominate over gravitational ones. A bacterium experiences water, as we might experience honey-thick, sticky, and resistant. Gravity barely affects such tiny creatures directly, yet even they evolved mechanisms to sense and respond to it. Many bacteria contain magnetosomes, tiny iron crystals that align with Earth's magnetic field, helping them determine up from down and navigate to optimal depths in the water column. As life grew larger and more complex, gravity became an increasingly important selective pressure. The first multicellular organisms faced new challenges: how to maintain structural integrity against gravity's pull, how to transport nutrients throughout their bodies against the downward force, how to position themselves optimally in the water column. These challenges drove innovations that would define the major branches of life's tree. Plants embarking on the conquest of land 450 million years ago faced gravity's full force for the first time. In water, buoyancy supports much of an organism's weight, but on land, structures must bear their entire mass. The evolution of lignin, the complex polymer that gives wood its strength, was a direct response to gravitational challenge. This remarkable molecule, which can support columns of water hundreds of feet high in giant trees, allowed plants to grow tall, compete for sunlight, and create the forests that would transform Earth's climate and provide new habitats for animal evolution. The vascular systems of plants represent one of evolution's most elegant solutions to gravity's challenge. Xylem vessels, tubes formed from dead cells, transport water from roots to leaves through a combination of capillary action, root pressure, and transpiration pull. In the tallest trees, water must travel over 100 meters vertically against gravity's constant opposition. The physics of water transport sets ultimate limits on tree height around 130 meters, where the energy cost of lifting water higher exceeds the photosynthetic benefit of additional height. Root systems evolved not just to absorb water and nutrients, but to anchor plants against gravity's overturning moment. The deeper and wider a root system, the taller a plant can grow without toppling. The buttress roots of tropical trees, the extensive shallow root networks of desert plants, the pneumatophores of mangroves. Each represents a different engineering solution to the problem of stability in different gravitational situations. Gravitropism, the ability of plants to sense and respond to gravity, involves sophisticated cellular machinery. Specialized cells called statocytes contain dense starch granules called statoliths that settle to the bottom of the cell, indicating the direction of gravity's pull. This information triggers differential growth hormone distribution, causing roots to grow downward, positive gravitropism, and shoots to grow upward, negative gravitropism. Even in the microgravity of space stations, plants struggle without this gravitational guidance, growing in confused spirals. Animals conquering land faced their own gravitational challenges 400 million years ago. In water, the buoyancy force supports most of an animal's weight, allowing jellyfish to grow meters across, with bodies that are 95% water, and enabling whales to reach sizes impossible on land. But emerging onto shore meant supporting their entire body weight against gravity's downward pull. The evolution of the vertebrate skeleton, with its complex architecture of bones, cartilage, and connective tissue, represents one of life's great engineering achievements in response to gravitational force. The transition from fin to limb involved profound restructuring driven by gravitational demands. Fins, excellent for pushing against water, couldn't support body weight on land. The evolution of weight-bearing limbs required strengthened bones, new joint configurations, and reorganized muscle attachments. The tetrapod limb, with its characteristic bone structure of humerus, radius, and ulna, carpals, metacarpals, and digits, became evolution's solution for terrestrial locomotion. This same basic structure, modified countless ways, supports creatures from salamanders to elephants. The vertebral column evolved from a simple notochord into a complex structure of vertebrae, discs, and ligaments capable of supporting body weight while maintaining flexibility. The S-curve of the human spine, unique among primates, distributes gravitational stress and acts as a shock absorber for our upright posture. Each vertebra is an engineering marvel, with load-bearing bodies, protective neural arches, and processes for muscle attachment, all shaped by millions of years of gravitational selection pressure. Bone itself is a remarkable material that evolved in response to gravity's demands. Its composite structure of flexible collagen fibers, reinforced with rigid calcium phosphate crystals, creates a material that's both strong and resilient. Living bone constantly remodels itself in response to gravitational stress, growing denser where loads are highest and lighter where they're reduced. This process, called Wolff's law, means that bones adapt their structure to their gravitational environment throughout an organism's lifetime. The cardiovascular system represents another evolutionary response to gravity's challenge. In water, blood pressure differences are minimal, but on land, gravity creates significant pressure gradients. A giraffe's heart must generate enough pressure to pump blood 6 feet upward to its brain, requiring specialized valves and vessel structures to prevent blood from pooling in the legs. When a giraffe lowers its head to drink, special pressure regulating mechanisms prevent catastrophic blood flow to the brain. Birds evolved unique adaptations for dealing with gravity during flight. Their hollow pneumatic bones reduce weight while maintaining strength. The fusion of many bones creates rigid structures that can withstand the stresses of powered flight. The keeled sternum provides attachment for massive flight muscles that can comprise 30% of a bird's body weight. Even their respiratory system, with air sacs extending into bones, represents an adaptation that reduces density while improving oxygen delivery for the metabolically demanding act of flying against gravity. The evolution of flight itself, achieved independently by insects, pterosaurs, birds, and bats, represents life's repeated attempts to overcome gravity's constraints. Each group found different solutions: insects with their exoskeletons and direct flight muscles, pterosaurs with their membrane wings supported by elongated fourth fingers, birds with their feathered wings and specialized skeletal adaptations, bats with their membrane wings stretched between elongated finger bones. Flight's evolution demonstrates both gravity's limiting force and life's persistent innovation in overcoming it. Marine mammals returning to the ocean faced the reverse challenge, readapting to an environment where gravity matters less but pressure increases dramatically with depth. Whales evolved specialized adaptations for dealing with pressure changes during deep dives, including collapsible rib cages, reduced air spaces, and blood chemistry that resists nitrogen bubble formation. Their massive size, impossible on land due to gravitational constraints, becomes an advantage in water where buoyancy supports their weight. The inner ear's evolution showcases biological gravity detection at its most sophisticated. The vestibular system, present in all vertebrates, contains semicircular canals detecting rotational acceleration and otolith organs detecting linear acceleration and gravity. Tiny calcium carbonate crystals, called otoconia, resting on hair cells in the utricle and saccule, shift with gravity's pull or acceleration, sending signals about body position and movement to the brain. This system is so sensitive it can detect tilts of less than 1 degree. Human bipedalism represents one of evolution's most dramatic responses to gravitational challenge. Walking upright required extensive anatomical reorganization. A repositioned foramen magnum, where the spine enters the skull, a shortened and broadened pelvis, extended lower limbs, an arched foot, and numerous muscular and skeletal adaptations. The energy efficiency of bipedal walking, despite its gravitational challenges, freed our hands for tool use and may have been crucial in human brain evolution. The human foot alone contains 26 bones, 33 joints, and over 100 muscles, tendons, and ligaments, all working together to support body weight, absorb impact, and provide propulsion against gravity. The medial longitudinal arch acts as a spring, storing and releasing energy with each step. This complex structure evolved from the grasping feet of our arboreal ancestors into a specialized platform for bipedal locomotion. Pregnancy and birth in humans demonstrate extreme gravitational challenges. The evolution of bipedalism narrowed the pelvic canal just as increasing brain size demanded larger infant heads. This obstetric dilemma led to humans giving birth to relatively underdeveloped infants compared to other primates, requiring extended parental care. The mechanics of human birth, with the infant rotating as it passes through the birth canal, represents a complex solution to gravitational and anatomical constraints. At the cellular level, gravity influences fundamental biological processes. Cells can sense mechanical forces, including gravity, through mechanosensitive ion channels that open or close in response to membrane deformation. The cytoskeleton, the cell's internal scaffolding, reorganizes under gravitational stress. In microgravity experiments on the International Space Station, cells show altered gene expression, modified protein production, and changes in proliferation rates, demonstrating that even single cells have evolved to function in Earth's gravitational field. Bone loss in astronauts reveals how dependent our physiology is on constant gravitational loading. Without gravity's stress, bones lose density at rates of 1 to 2% per month, similar to severe osteoporosis. Muscles atrophy, particularly the anti-gravity muscles that maintain posture. The cardiovascular system deconditions as the heart no longer needs to pump against gravity. These changes demonstrate that our bodies are finely tuned to Earth's gravitational environment. The study of extremophiles, organisms living in Earth's most challenging environments, reveals gravity's role in setting limits for life. In deep ocean trenches, where pressure from the overlying water column is crushing, specialized bacteria thrive with pressure-resistant proteins and modified cell membranes. At the other extreme, tardigrades can survive in the vacuum of space, entering a cryptobiotic state where metabolic processes nearly cease, demonstrating life's ability to temporarily escape gravitational and atmospheric constraints. Trees represent perhaps the most visible ongoing battle against gravity. The tallest trees, the coastal redwoods of California, can exceed 115 meters in height. At these extremes, the energy cost of pumping water to the crown approaches the energy gained from photosynthesis at that height. The theoretical maximum tree height, around 130 meters, is set by the physics of water transport against gravity. Every tree on Earth lives within this gravitational limit, their forms shaped by the constant need to support their mass and transport water skyward. Animal locomotion strategies directly reflect gravitational constraints. Small animals like insects can walk on walls and ceilings using van der Waals forces that overcome their minimal weight. Medium-sized animals must use specialized adaptations like the gecko's hierarchical adhesive structures. Large animals are confined to the ground, their locomotion strategies optimized for energy efficiency against gravity. The relationship between body size and locomotion mode demonstrates gravity's role in determining what's physically possible for organisms of different scales. The evolution of seeds and spores represents life's solution to dispersal under gravitational constraints. While gravity pulls everything downward, plants evolved numerous mechanisms to spread their offspring: wings and parachutes that slow descent and allow wind dispersal, hooks and burrs that attach to passing animals, explosive pods that launch seeds away from the parent, and floating structures that enable water dispersal. Each strategy represents a way to overcome or exploit gravity's downward pull. Circadian rhythms, while primarily driven by light cycles, are also influenced by gravitational cues. Many organisms use the interaction between light and gravity signals to maintain proper orientation and timing. Plants integrate gravitropic and phototropic responses to optimize growth direction. Animals use gravity as a reference for maintaining balance and posture throughout daily activity cycles. The interplay between gravitational and other environmental cues demonstrates the deep integration of gravity sensing into biological systems. Migration patterns of many species incorporate gravitational energy considerations. Birds migrating over mountain ranges time their flights to take advantage of thermal updrafts that provide lift against gravity. Salmon swimming upstream to spawn must overcome both current and gravity using tremendous energy reserves accumulated in the ocean. Monarch butterflies on their multi-generational migration use gliding and thermal soaring to minimize energy expenditure against gravity during their thousands-mile journey. The evolution of echolocation in bats and dolphins occurred in three-dimensional environments where gravity provides a constant directional reference. These animals create detailed mental maps, incorporating gravitational orientation, using sound to navigate in darkness or murky water where visual cues are limited. Their ability to process echoes, while accounting for their own movement through gravitational fields, represents sophisticated neural processing shaped by millions of years of evolution. Biomineralization, the process by which organisms produce minerals, is profoundly influenced by gravity. Shells, bones, and teeth must withstand gravitational forces throughout an organism's lifetime. The orientation of mineral crystals, the density of mineralized tissue, and the architectural structure of shells all reflect gravitational optimization. Mollusks produce shells with logarithmic spirals that distribute gravitational stress efficiently. Coral polyps build reefs that can withstand both gravity and wave action, creating structures visible from space. The evolution of consciousness itself may have been influenced by the need to model and predict gravitational effects. Mobile animals need to anticipate how gravity will affect their movements and the behavior of objects in their environment. The ability to mentally simulate trajectories, understand object permanence, and predict physical interactions all require an implicit understanding of gravity. Our intuitive physics, evolved over millions of years, is fundamentally shaped by life in a gravitational field. As we look to the future of life beyond Earth, gravity emerges as a fundamental constraint on biological possibility. Mars's gravity, 38% of Earth's, would allow for different organismal architectures, but might pose challenges for Earth-evolved life. The Moon's 1/6 gravity would permit even more extreme forms, but would require fundamental adaptations in every biological system. Generation ships travelling to other stars would need rotating sections to provide artificial gravity, acknowledging that our biology is inextricably linked to the gravitational environment in which we evolved. In the depths of space 5 billion light-years from Earth, a dying star exploded with the brightness of 5 billion suns. The light from this Type Ia supernova, travelling for eons across the expanding cosmos, finally reached telescopes on a small blue planet where astronomers were conducting what they thought would be a routine survey. But when they analysed the data in 1998, they discovered something that shook the foundations of cosmology. The universe's expansion wasn't slowing down. As gravity should cause it to do, it was accelerating. This discovery would win the Nobel Prize and reveal that gravity, the force we thought we understood best, holds mysteries that will determine the ultimate fate of everything that exists. Dark energy, the name given to whatever causes this cosmic acceleration, represents one of the most profound puzzles in physics. It comprises approximately 68% of the universe's total energy density, yet we have almost no idea what it actually is. Unlike dark matter, which clusters around galaxies and affects their rotation, dark energy appears uniformly distributed throughout space, pushing everything apart with a gentle but relentless pressure that grows stronger as the universe expands and space itself increases. The discovery emerged from observations of Type Ia supernovae, stellar explosions that serve as standard candles because they all reach approximately the same peak brightness. By measuring how dim these supernovae appear, astronomers can calculate their distance. By analysing their light's redshift, they can determine how fast they were receding when the light was emitted. Two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, expected to measure how much the universe's expansion was decelerating. Instead, they found acceleration beginning about 5 billion years ago. The cosmological constant, which Einstein called his greatest blunder when he removed it from his equations, suddenly seemed prescient. Einstein had introduced this constant to maintain a static universe, before Hubble discovered cosmic expansion. Now it appeared he might have been right for the wrong reasons. There really was something like a cosmological constant, but instead of balancing gravity to create a static universe, it was overwhelming gravity to accelerate expansion. The nature of dark energy remains almost completely mysterious. The simplest explanation treats it as a property of space itself, vacuum energy, that creates negative pressure. Quantum field theory predicts that empty space should teem with virtual particles constantly appearing and disappearing, contributing energy even to perfect vacuum. But when physicists calculate the expected vacuum energy density, they get a value 10^120 times larger than what we observe, the worst prediction in the history of science. Alternative theories abound, each with profound implications for gravity's future role in the cosmos. Quintessence models propose that dark energy comes from a dynamic field that changes over time, unlike the cosmological constant which remains fixed. These scalar fields, similar to the hypothetical inflaton field that drove cosmic inflation, could have different values at different times and places, making the universe's fate less certain than a simple cosmological constant would imply. Modified gravity theories suggest that perhaps dark energy doesn't exist at all. Instead, gravity itself behaves differently on cosmic scales than general relativity predicts. These theories must carefully match all of general relativity's successful predictions while explaining cosmic acceleration without dark energy. Some propose extra dimensions that modify gravity at large distances. Others suggest gravity leaks into higher dimensions on cosmic scales, weakening its attractive force and allowing acceleration. The competition between gravity and dark energy will determine the universe's ultimate fate. Currently, gravity dominates on scales smaller than galaxy clusters, holding together solar systems, galaxies, and clusters against dark energy's expansive push. But as the universe expands and matter dilutes, while dark energy's density remains constant, dark energy's influence grows ever stronger. We live in a special epoch when both forces have comparable influence on cosmic scales. If dark energy is truly a cosmological constant, the universe faces a big freeze or heat death. Galaxies will continue accelerating away from each other until in about 100 billion years, all galaxies outside our local group will disappear beyond the cosmic horizon. The observable universe will shrink even as the actual universe expands infinitely. Stars will exhaust their fuel, black holes will evaporate through Hawking radiation, and the universe will approach a state of maximum entropy, cold, dark, and essentially empty. The Big Rip presents an even more dramatic possibility if dark energy's strength increases over time. In this scenario, dark energy eventually overwhelms all forces, not just gravity. Galaxy clusters would be torn apart first, then galaxies themselves. As dark energy's dominance grows, it would overcome the forces holding stars and planets together. In the final moments, even atoms would be ripped apart as dark energy defeats the electromagnetic force. This cosmic apocalypse could occur in as little as 20 billion years if certain models prove correct. Cyclic universe models offer a less final alternative, suggesting our universe undergoes repeated cycles of expansion and contraction. In these models, dark energy might reverse its effect or decay into matter and radiation, eventually allowing gravity to halt and reverse expansion. The universe would contract in a big crunch, possibly bouncing to begin a new cycle. Each cycle might last trillions of years, with gravity and dark energy taking turns dominating cosmic evolution. The multiverse implications of eternal inflation suggest our universe might be one of infinitely many, each with different values of dark energy and gravitational strength. In this vast ensemble, most universes might expand too quickly for gravity to form structures, or collapse too quickly for complexity to evolve. We observe the values we do because only in universes with near-perfect balance between gravity and dark energy could observers like us exist to measure them. Current observations are refining our understanding of dark energy with unprecedented precision. The Dark Energy Survey has mapped hundreds of millions of galaxies, measuring how cosmic structure evolved over billions of years. The Euclid Space Telescope, launched in 2023, will observe billions of galaxies to create the most detailed, three-dimensional map of the universe ever made. These surveys test whether dark energy has remained constant or evolved over cosmic time. Gravitational wave astronomy opens new windows on gravity's future. As black holes merge throughout cosmic history, their gravitational waves carry information about the universe's expansion rate at different epochs. Future space-based detectors like LISA will observe supermassive black hole mergers from the early universe, providing independent measurements of how dark energy and gravity have competed over cosmic time. The discovery of gravitational lensing by dark energy, where cosmic voids create subtle distortions in galaxy images, provides another probe of this mysterious force. The integrated Sachs-Wolf effect, where cosmic microwave background photons gain or lose energy traversing large-scale structures, reveals the competition between gravity's structure formation and dark energy's expansion. These subtle effects, barely detectable with current technology, will become powerful probes with next-generation instruments. Quantum gravity theories might ultimately explain dark energy as an emergent phenomenon from the fundamental structure of spacetime. If spacetime is discrete at the Planck scale, dark energy might arise from the quantum properties of spacetime itself. String theory's landscape of possible universes might explain the observed value through anthropic selection. Loop quantum gravity's discrete spacetime might naturally produce effects mimicking dark energy. The holographic principle suggests a deep connection between gravity, information, and dark energy. If our three-dimensional universe is encoded on a two-dimensional boundary, dark energy might relate to the information processing capacity of this boundary. As the universe expands, the boundary area increases, potentially driving acceleration through holographic mechanisms we don't yet understand. Laboratory experiments are beginning to probe dark energy's properties. Atom interferometry experiments search for fifth forces that might be associated with dark energy fields. Tests of gravity at microscopic scales look for deviations that might reveal extra dimensions or modified gravity. While dark energy's effects are negligible on laboratory scales, precision measurements might detect subtle signatures of new physics. The future of gravitational physics will likely require revolutionary conceptual advances comparable to those of Newton and Einstein. Just as Newton unified terrestrial and celestial gravity, and Einstein revealed gravity as curved spacetime, future theories might show dark energy and gravity as aspects of something even more fundamental. The solution might require abandoning cherished assumptions about the nature of space, time, energy, or information. Technological advances will enable observations currently beyond our reach. Gravitational wave detectors, sensitive to primordial waves from cosmic inflation, could reveal quantum gravity's signature. Telescopes capable of observing the first stars and galaxies will show how gravity assembled structure in dark energy's presence. Precision measurements of fundamental constants over cosmic time might reveal whether the laws of physics themselves evolve. The philosophical implications of dark energy's dominance challenge our cosmic perspective. If acceleration continues, the observable universe will become increasingly isolated, with future civilizations unable to observe the cosmic microwave background or distant galaxies that revealed the universe's history to us. They might conclude they live in a static, eternal universe, unaware of the Big Bang or cosmic expansion. Our epoch might be uniquely suited for understanding cosmic history. The role of intelligent life in the universe's gravitational future remains speculative but intriguing. Advanced civilizations might harness dark energy for cosmic engineering projects. They might create baby universes with different gravitational properties. They might even find ways to alter dark energy's strength, changing their universe's fate. While highly speculative, such possibilities remind us that gravity's future might not be entirely determined by natural processes. As we contemplate gravity's future, we're reminded of how this humble force that drops apples and holds us to Earth connects to the grandest questions of existence. The same equations describing planetary orbits govern the universe's expansion. The same curvature of spacetime that bends starlight determines cosmic destiny. Gravity, the first force humans recognized and the last to be understood quantum mechanically, continues revealing surprises that reshape our understanding of reality. The coming decades will likely bring revolutionary discoveries about gravity and dark energy. New observations might reveal dark energy's nature or show it changing over time. Quantum gravity theories might explain the cosmological constant problem. We might discover modifications to general relativity on cosmic scales or extra dimensions affecting gravity's strength. Each discovery will refine our predictions of gravity's role in the universe's future. The ultimate fate of gravity depends on dark energy's true nature, which remains one of science's greatest mysteries. Will gravity continue its eternal struggle against dark energy's expansion, gradually losing influence as the universe empties and cools? Will dark energy strengthen until it tears apart all structures gravity has built? Or will some unknown physics intervene, creating futures we haven't imagined? The answer will determine whether the universe ends in ice or fire, whether new cycles of cosmic evolution await, or whether something entirely unexpected lies ahead.